so it's very quiet in here. That's good. I want to wish you all welcome to this symposium that we called Light at the Nanoscale. My name is Bo Albinsson, and I'm the director of the Nanoscience Excellence Initiative at Chalmers. And I'm one of the organizers of this conference. The other organizers being the Materials Science Area of Advance and the Molecular Frontiers Foundation. So Light at the Nanoscale is the theme, and of course this time of the year it's about what you can get in Sweden. It's light at the really nanoscale, to be honest. I want to direct a special welcome to the speakers that we have convinced to come here to Sweden in this cold time of the year, so very welcome, and we look forward to listen to your talks. Another very special welcome is also to the high school students from all over Sweden and a few from Denmark as well. So very welcome to join us here at Chalmers for these 2 days. So I will not speak anymore. I will hand over the microphone to the Chalmers president, Professor Stefan Bengtsson. So please, Stefan.
Thank you, Bo. Good morning, everyone. I'm Stefan Bengtsson, and I'm the President Director of Chalmers University of Technology. And it's, of course, also my pleasure to welcome you all to this symposium, Light at the Nanoscale, from molecules to quantum computing. And in particular, of course, I say welcome to all of the high school students which are in the room here, coming from all over Sweden, from the city of Ystad in the south to the city of Boden in the north. And in addition, we also, as Bo said, had a number of students from Denmark. So you're all very, very welcome here. And I certainly hope that you will find the days interesting here and having a view of few areas of science, but also have the opportunity to discuss with the excellent speakers that we have here. Of course, welcome also to all of our excellent speakers. We really appreciate you taking the time to come here to join us for this seminar. Chalmers University of Technology. We are today some 3,000 employees, 10,000 students. We are educating engineers, architects. We're also educating people for the maritime sector, sea captains and chiefs, and we are actually also educating teachers as a part of our master's program. Chalmers is located here at Campus Johanneberg, but also at Lindholmen across the river. We are one of the few Swedish universities named after a person, William Chalmers. He was the director of the Swedish East India Company. And in his will, when he passed away 1811, he donated a fortune to start an engineering school for poor children that has learned to read and write. That was the starting point of Chalmers, 1829. 10 students and 3 teachers, so we have grown a bit since there. Chalmers is roughly 75% of our activities is research and PhD education, and 25% is the education of engineers, architects, etc. Academic excellence, high quality in what we are doing is of course very important, but we also having a well-developed, and we all the time continue to develop it, method, way of working, and other ways we have organized ourselves to be able to work together with industry. So we have an extremely strong collaboration with industry, and we are co-producing results together with many large companies, and that is also of course so that in our education we give the companies, we use them also as teachers and for visits, projects, etc. at the companies. This symposium is co-organized by Chalmers, by the Nano Excellence Initiative and the Material Science Area of Advance at Chalmers, and the Molecular Frontier Foundation. It's a seminar in a series of seminars that has been held on various topics, and this certainly looks as a very broad team today, but very challenging and interesting team to discuss. We mentioned here the excellence initiatives, areas of advance, etc. This is structures that we have built to be able to work together across different disciplines. So they are sort of a matrix structure going across Chalmers departments. Bringing researchers, students from different departments together, forming some kind of focal teams and forming platforms for our industrial collaboration. Our society, as well as mankind, is facing large challenges. For sure, we know we need more knowledge, we need more research, we need high-quality education, thereby preparing young people to be able to address these large challenges in the future. And I'm optimist. By doing this way with research and education, we will find ways of solving the challenges and being able to have a planet which can accommodate the population and which can give all humans reasonable life there. So knowledge and research is important there. So again, very much welcome here for all of you high school students. Take the opportunity here, you get a glimpse of some science. Of course, I hope that you will consider Chalmers when you are considering your own higher education. So you will always be welcome here also as students in the future, and I hope that all of you will consider that. So I wish you good discussions, and I say again, welcome here, and thank you for being here. Thank you very much. We will now have another short introductory address, so I would like to ask Professor Bengt Nordén to come up on stage. You have already seen him in the movie, so please, Bengt.
Okay, thanks. Well, I also say warmly welcome to all of you and to this exercise. When we discussed, maybe I should say a few words about Molecular Frontiers, which started in 2006, and you could just Google it. The homepage is interesting. You could see a lot of earlier movies, earlier talks and so on. And you could also see who are our advisory board. That's a heap of people, I think 30 people, and many of them are Nobel laureates. So the exercise of Molecular Frontiers is, we used to say that it has two phases. One is a very serious scientific one, where we try to identify the breakthroughs at the research frontiers and explain it. And you know, the Royal Swedish Academy of Sciences is awarding the Nobel Prizes, science prizes in physics and chemistry, for instance. And they are helped by getting this information collected. But the other phase is one where we try to go out into the society and mainly to young people to explain not only molecules and chemistry. That was how it all started, an idea by Jean-Marie Lehn that chemistry is the least popular topic on the scheme. I think handicraft in wood was a little lower, but so Jean-Marie Lehn thought that maybe we could do something, and so this was in 2006. Since then, the concept of molecule is rather a vehicle into science. It could be all kinds of science. Today's topic, which is very much on light and quantum mechanics, is something that shows the broadness of science, and it should also show, and I address the speakers here, try to explain why science is useful. We were a little concerned that the content of quantum mechanics might go over the heads of many of you, but then I can comfort you the same. A big scientist and a Nobel laureate, Richard Feynman, said once that if you understand quantum mechanics, or if you think you understand quantum mechanics, then you don't understand quantum mechanics. So with that, I have no further information. Per Thorén here, who is in charge, will tell you more details later. But as I said, Google Molecular Frontiers and you find our homepage. So we look forward to a challenging program. And again, warmly welcome all of you. Thank you.
Hello, my name is Per Thorén. I'm COO of Molecular Frontiers, so I'm in charge of operations. So I have some practical things for you. Some of you got caught in the queue downstairs, so you can register in the coffee break, and there's also a wardrobe that some of you may not have had the chance to visit yet, but it will be open all day, and also in the evening, because high school students, we are treating you to dinner tonight. I hope you can all come. The Chalmers students will take care of you for that after the talks have finished today. But we'll get back to that. And we're going to try to get all of you actually up on stage for a photo. It will be fun. Another thing, during this autumn, the material science researchers here at Chalmers, the PhD students and the professors have had a contest, a photo contest, where they submit photos of their work, and we actually have a very nice prize for the winner. It's a research trip anywhere in the world. So it's very important that we get the right winner, and the 5 finalists are displayed outside here. I hope you have noticed that. And we want you all to vote so we get the right winner. There are instructions outside. You do it on your smartphone. Okay, and I think that's it. The restrooms are also downstairs if you need to go. With that, I would like to hand over to our first chair, Göran Vendin.
Thank you very much. My name is Göran Vendin, and I'm a professor at microtechnology and nanoscience up here at Chalmers. So I have the pleasure to chair the first 2 talks this morning. I'm pleased then to introduce you to Professor Emanuel Bloch from Munich. Emanuel is the scientific director of the Max Planck Institute in Garching, which is in the north part of Munich. And I've known him for quite some time, and he's leading really the best group in the world in quantum, in atomic condensates, which trapped in laser traps. And with that, you can make very, very advanced studies of artificial and real quantum matter. And that is what is going to be the title and the topic of this talk, which is quantum matter under the microscope. So please.
All right. Okay, so thank you very much for having me here. It's really wonderful to be here with so many young faces here. And I hope with the talk, I can convey to you the excitement we have in our research, and maybe it's something you will pick up later in the stage. And quantum mechanics, as was mentioned, sounds bizarre sometimes, but for me it was one of the most intriguing things I could during my studies as a physicist. So let me tell you what we're doing and how we're trying to explore the world of quantum physics in our labs in Munich. And so for that, I try to give you an overview, first of all, what we're going to talk about. So I'll give a brief interview doing what we're doing. Then I'll talk a little bit about why it's difficult and how we solve this problem and what tools we have available to do that. And then also tell you a little bit about the applications this kind of research has. So when you look at materials, we're especially interested today in exciting materials with special properties, for example, that have this phenomena of superconductivity, that are special magnetic properties which we can use for data storage. So we really want to predict what kind of properties a material has. Now, that's actually quite difficult because even though we know the rules by which these electrons or atoms in a material play very precisely, it's very difficult to solve the equations and predict what the collective behavior of those atoms and electrons is going to be. But that, because of course, this would then give us, huge handle on designing new materials. So what can we do to solve this problem, and why is it actually so difficult? So let me explain that to you. Let me imagine, let's take a hard drive that you could have on your computer, and there's data stored on your hard drive. Let's say we have the ultimate density in the end of storage, where we could store information, zeros and ones, in these little magnets that can point up or down. We call these the spins of the electrons or atoms. So think of them just as magnet pointing up or down. If it points up, then it's a 0. If it points down, then it's a 1. And then, of course, your hard disk could be in this state or that state, or there's some information stored in it, so the atoms would be in this kind of configuration corresponding to the zeros and ones on your hard disk. Now, that's a classical system, and we know how to handle that very well. But in the quantum world, we describe states of matter that materials can assume by this wave function psi. So physicists like to use this big psi to describe the states that matter can assume. And in contrast to the classical world, the new thing we have in the quantum world, that a system can be simultaneously in different configurations. So in the classical world, you can only be in this configuration or that configuration, but in the quantum world, you can be simultaneously in all of those different configurations. And that gives you tremendous power, tremendous potential. You're going to hear more about that tomorrow in the part on quantum computing. But it also confronts scientists with a tremendous challenge, because now let's imagine you just want to store the state of your system on a computer, and you have n particles. Then it turns out that you have 2 to the n configurations, which can be a huge number if n is already pretty small. Yeah? So a huge number of configurations, and you need to store all those numbers here to just write down what the state of the system actually is. You haven't done any calculation yet, you've just actually stored the state of the system. And that means that even with the best supercomputers we have today, we're not able to tackle this problem, because they run out of memory extremely fast. And it's something we probably cannot hope to solve with even more powerful classical supercomputers, because every time we want to simulate, we want to store 1 particle more in the memory of that computer, we need to double the memory of that computer, which is because of this exponential scaling. And if we would just think about a modest size of a system of only 300 particles, 300 of those spins of those magnets pointing up and down, we would need a memory storage which is larger than the entire number of protons we estimate to be in the entire universe today. So that shows you that that's actually a difficult thing to do. So of course I should say, physicists have been clever, and material scientists, in devising approximate solutions to this problem and still to do calculations. And that works well when typically the system only explores a small part of this large configuration space I talked about. But as soon as you're faced with, for example, dynamical evolutions or special kind of materials which explore this entire configuration space, which we call in physics the Hilbert space of the system, then you really have a problem dealing with this on these classical computers. So what can we do? Well, we just try to think out of the box and come up with a completely different solution to the problem. And we try to build a quantum system itself which can solve the quantum problem. Okay? And this we can do since a few years now, because we now have fantastic control over individual quantum objects, such as single atoms, ions, photons, or you'll hear superconducting circuits tomorrow, which have been ultimately controlled at the quantum limit today. And now we can follow up with Richard Feynman's idea and say, well, why not take these fantastically controlled single quantum systems, build an artificial quantum system out of it to study quantum matter and to solve these outstanding problems, for example, for material science. And this is what people are doing in very different platforms, with ions in traps, with atoms, with superconducting circuits that you'll hear about more also tomorrow. So what are we trying to do? Let me put this in a nutshell for materials. Here's a real material. It's really tiny, right? You hardly see it, and that's reality. Typically, the distances between atoms in a real material are on the angstrom scale, 10 to minus 10 meters, really, really small scale, 10,000ths of a micrometer, and it's really hard to look into these materials. That's why, of course, people are building really good microscopes to view into these materials, and that's, for example, why we're building the XFEL in Hamburg, X-ray laser, to look into these systems. Now, we're taking a completely different approach. We're trying to say, well, if it's so hard to look into this really small material, why don't we make it just bigger? Why don't we just scale everything up in this material, so now everything is not on the angstrom scale, but everything is 10,000 times bigger, so now you have micrometer distances between the atoms, and now you can actually, at a micrometer scale, you can actually just use conventional optics, a good lens, to look into this material. The advantage that has is also that the processes that happen in this real material, which typically are extremely fast, which happen on the picosecond or femtosecond time scale, are slowed down in this enlarged material, where now everything happens at much slower time scales, so we can actually conveniently observe what's going on in the system. So this works in the end, because in quantum mechanics, the only thing that counts if you want to observe this collective quantum behavior of matter is this ratio of what we call the de Broglie wavelength, which tells us what kind of wave structure these particles have, divided by the distance between the particles. So if we make the distance between the particles 10,000 times larger, then in order to observe the same quantum behavior, we have to make this lambda, this thermal de Broglie wavelength, also a factor of 10,000 larger. How do you make lambda large, this waviness of the atoms, of the electrons? Well, you actually, turns out, you have to cool down to extremely low temperatures. That's what changes lambda, and that's where the catch is. We really have to cool down to few nanokelvin or microkelvin, so that's just a millionth degree of a Kelvin above absolute zero. That's a million times colder than outer space to reach these conditions where that is actually met. So that's what we have to achieve, but then we can look at the same behavior that happens in real materials in these artificial quantum systems. And then the challenge, what we do then in the lab, is basically we try to build these model systems, these enlarged materials. We try to run them in the lab, see what they do, and then kind of feedback from this experience we gain on these artificial systems to learn something for real materials, how we can design better real materials with this knowledge. What's also cool, actually, is that you're not only restricted to what materials you can design today, you can let your imagination run a bit wilder and design crazy materials that don't even exist yet in nature, and just look what kind of properties they actually have. Let me skip that. So here are a few ways how to do that with atomic systems, atomic platforms. So there's these ion traps I talked about before. Here you can see a string of 50 individual ions. Each of those fluorescent spots is a single ion. That's an atom where you removed one electron, stored in an electromagnetic cage, which is shown here, and that's a photo of these ions. And you can address individual ions, you can make them interact with each other by shining laser pulses onto these systems. Another cool system that people are exploring right now is actually atoms trapped in the focus of a laser beam. We call this an optical tweezer. So it's just focusing down a laser beam to very small scales, and the focused beam will create a trapping potential in which you can trap atoms. And here's a picture from Antoine Brouvet's group where he trapped atoms in three-dimensional structures. You can go onto his website and you can actually see these things rotate, where you see, for example, well, as a French person, he likes to make the Eiffel Tower in 3 dimensions. So you can look at it out of these atoms placed on these corners of these tweezers. The system we're using to make these structures are optical crystals, how we call them, that we generate by interfering light beams. So here's actually a light pattern, that's actually a real experiment, light pattern created by overlapping 5 laser beams from different configurations, from different directions. And you can see the beautiful structure that emerges from that. It's not a calculation, it's really just recorded what happens when you interfere those different laser beams, and you look what you get. And you see you get this beautiful complex crystal structure, which is basically defect 3, and now we can basically load cold atoms very gently into this potential and trap them and study their behavior in these optical potentials. Now, the advantage of the method is, of course, if you want to synthesize a new material, a new crystal structure, you just have to interfere the laser beams under slightly different angles, and you get a new crystal with this. With that, you can study, as we'll see, about a few thousand particles in these systems and observe them actually also. So actually, if you want to know how this picture was done, and you want to actually look at a lot of very nice optics experiments as well, I highly recommend to you to go to Ted Hensch's YouTube channel. His name is Superlaser123. So there are beautiful optics experiments there, and also how this was generated. And let's make him a 1 million YouTube subscriber, so he gets this YouTube medal out of this. Okay, so we trap these atoms, and we create these quantum states of these different configurations that I talked about. Now, what happens if we make a photo of such a system? Again, remember, we have this psi, and the system can be in different configurations at the same time, as we said. And let's imagine I could take a photo of the system. A quantum system reacts very strange when you take these photos. Actually, this wave function, as we say, collapses. So now you basically only end up with one of those configurations randomly, and you cannot predict which one you're going to see, and this is the one you're going to actually see in the photograph of the system. Okay, so this is what we're going to see, but I cannot predict to you a priori which one I'm going to see. So this is one of the things that quantum mechanics can't tell us, but quantum mechanics can tell us how probable it is that those different configurations occur in these systems. And that's a very powerful way of observing these systems. And here's actually an image that this really works. So here's this optical crystal formed by interfering those different laser beams on top of each other. And then we shine in light to make the atoms fluoresce. So they light up like small light bulbs. And each individual kind of light bulb here, bright spot here, is indeed an individual atom trapped in this optical crystal in vacuum. Okay, so it's just held by the light field in the vacuum chamber in free space, and we're taking photos of them, and we can see each one of them actually with really good signal-to-noise ratio. We can actually also control them. We can go in with these lasers and also control the states of those atoms and rearrange them in arbitrary positions. And well, again, as physicists, we love this psi, so just as a demonstration object we showed, we could make this psi out of 26 individual atoms placed in this optical crystal of light. We can do this for the experts, actually also spin resolved, so that's really nice for these systems. We really know, thinking of these magnets, I said these atoms are like magnets pointing up and down. I can tell you where the magnet's pointing up, where it's pointing down, where there's a hole, where there are two atoms, and that's really a lot of very, very useful information we need to describe those materials and to characterize them in completely new ways. We also use light to paint potentials, more flexible potentials that we use to trap these atoms. And here you can see a few pictures that we generated by just shining laser light on these so-called digital mirror devices. This is the same thing that's actually in the projector back there that projects my slides onto the screen. It's an array of micro mirrors, small mirrors that you can tip and tilt, turn on and off, and that allows you to project arbitrary light patterns onto the screen, as you see. But for us, this is super useful because it means we can project arbitrary light patterns, trapping potentials onto the atoms, and have very kind of interesting configurations to study their behavior. For example, you could have two of these boxes. You fill one of the boxes with atoms, and then you connect them by this wire of light. So that's just light there in vacuum, and the atoms will flow through this wire of light from one box into the other box. And that's, of course, like an electron flowing through, a conductor, a small wire, and we can study the behavior of conductance, for example, as a function of different parameters in the system. We can control the interactions between these atoms to a very, very high degree. There are very many different ways of doing that, so I don't want to go into detail that. We can let them collide. We can use molecules, as in this symposium, so important to have these molecules interact with each other. Or we can use very highly excited atoms where an electron has been promoted to a very, very large distance away from the core, where it flies around this core at very large distances, and now two of those so-called Rydberg atoms interact very strongly. Or, I don't know, Thomas, you're not going to talk about this, I think. Are you talking about the cavities? Also, the cavities, we can modify interactions between atoms or molecules, as you'll see then also later in Thomas' talk, by placing them between two mirrors, where light bounces back and forth between those two mirrors, and each time it passes one of those atoms or molecules, it interacts with them, and we can have interactions between those particles over a long distance. Now, all of this is done in complete isolation from the environment. All these micro-Kelvin temperatures that I talked about, you might think, well, this must look awfully cold in your system when you go into the lab. You must see freezing things and stuff. You don't at all. The only thing we need is an extremely good insulation of our system from the environment. That's why we do all these experiments in vacuum chambers. Right? As you know from your windows, that give you kind of a good insulation, or your cup, you know, these cups which have a vacuum insulation. We do the same, we just evacuate the whole system, and then there's basically no thermal contact to the outside world. So we can create microkelvin cold clouds in these ultra-high vacuum vessels, and they're basically isolated completely from the environment. And that's a very nice setting to work with, actually. Very unique setting. This is complex. This is a view how this looks really in the lab in the end, okay, when people do the experiments. Our graduate students and master students do the experiments. We have a lot of lasers and optics that we need to control to make these potentials, to cool the atoms, which is then guided over here into this system where the actual vacuum chamber is, where we actually do the experiments that I showed you before. In the end, you know, when you've aligned everything, actually I should say, when sometimes students like you come and visit the lab, I think this is the optics storage room for us. You know, it looks like a storage room for all the optics, because there are just thousands of optics elements on there. But each one of those optics elements is really placed on purpose, and so it's really needed. And if you just misalign one of those mirrors, the whole experiment doesn't work anymore. Okay, so you really have to be very careful what you're doing, and you have to be a really good student to know how to align these things, how to bring it back to operation if something fails. But once everything is aligned, then it basically amounts to programming the system from the computer, running the program you want overnight, for example, and then basically picking off the data and analyzing the data in the next day. So what kind of physics can you look at this? I talked already about these material science problems, which I'll come back to in a second. One other problem you've heard about maybe from the realm of high energy physics is they were so excited of discovering this Higgs particle in high energy physics. Yeah? Turns out actually a very related, also a Higgs type particle, not the same as the Higgs particle in high energy physics, but one that basically obeys the same equations that we described for the high energy one, occurs at extremely low energy scales, at 20 orders of magnitude lower energy scales in these systems, and we could use these artificial quantum materials to study its behavior and to show its existence and settle a 20-year-old debate in physics whether such particles actually exist or not. Another pretty cool thing we could do, and I just give a few highlights and urge you to follow on this, maybe on your own then, is to create very strange states of matter. Here, in this case, we were able to create these negative absolute temperature states. So maybe you know from your school studies that in physics, actually temperature 0 Kelvin is supposed to be the absolute lowest temperature we can reach. But then there's something actually we can go below this negative, below this 0 Kelvin scale, and we did this for a gas of atoms, and that actually has extremely interesting properties, this gas. It can have anti-friction, it can basically allow you to violate Carnot engine theorem. So it has really unique properties, and actually that actually led to an important discussion going back to the foundations of statistical physics and thermodynamics, started by Gibbs already in 1902, on what the correct form of entropy we should actually use to derive temperature. So if you want to learn more about it, there are by now many web pages on that explaining this negative temperature experiment. Okay, we even made it into Fox News. Maybe that's not a reference you should use, but there are other pretty good ones. Actually, a very nice one I like, if you don't know this YouTube channel, is from the colleagues at Nottingham University. They have this channel called 60 Symbols, where they basically discuss complex physics phenomena, and they try to explain it in simple terms. And I was really blown away to see that by now, I think more than 800,000 people have watched this video to learn about what negative temperatures are, how we can understand them, what their properties are actually. All right, let's do a simple experiment with these, just to show you this quantum world. Let's do a simple experiment of these atoms. I call it our quantum horse race, where we try to put the atoms, align them in this lattice. And let's say we just allow them to move in the horizontal direction. In the other direction, we just make the lattice so deep that they just have to stay within their lane, and they can only propagate within their lane. Now, when you start them, when you let them evolve, one strange thing that these quantum horses do is they actually run in both directions. So they run backward and forward simultaneously. And in contrast to what this movie shows you, we never know which one's ahead of the other one. So in a classical world, of course, you can continuously watch what the horse race is doing. In the quantum world, you cannot. Remember, when you observe in the quantum world, you collapse this quantum state. It's not the same thing as before. So really, we only know the outcome of the race at the end where we take a photo of the system. Before, we have no idea which one of these atoms is ahead of the other one. And only when we take snapshots, we can actually, in the end, tell which one won the race. And here are pictures of that. So we can just, for example, align atoms along this line. We can let them run. You can see how they kind of propagate in this diagonal direction. And then, for example, we take a photo after a certain evolution time, and we see, okay, here are the atoms. Here's the fastest one that ran, for example, maybe in the backward direction, the fastest. And quantum mechanics tells us nothing which of those particles is going to win the race. We don't know. But quantum mechanics tells us if we repeat this experiment thousands of times, and I average the outcome of those experiments, what the probability of my particles after this race are going to be. And so this red curve that you see here, that's what quantum mechanics actually predicts, only probabilities of outcomes, not what we're going to observe in a specific outcome of the experiment. But when we actually see, when we do average our experimental data over thousands of those runs, we see actually very good agreement with this prediction from quantum mechanics. Here's an even nicer plot showing the orange curve is the prediction from quantum mechanics. The bars are our experimental data, thousands of shots, thousands of repetitions of this quantum race, and then looking what the probability distribution is to find an atom at a certain position in that lattice, and we can see we really have really excellent agreement with this evolution according to quantum mechanics. One kind of more complex thing I just want to mention, which was kind of for us a research highlight this year, is that we can use this to study far more complex behaviors. This was a very simple example. Actually, more complex behavior coming from the phenomena of superconductivity is to understand how actually these spin ups and downs interact with impurities in these systems. And that is believed to be the key solution to understanding the phenomena of high TC superconductivity. So basically, if I want to put this into a cartoon, let me put it into this cartoon here. You have in 2 dimensions this antiferromagnet where you have these spins pointing up and down, these blue and red particles, and then you put a single hole in there. You just remove one atom. And now you want to understand actually how does this single impurity move in this so-called antiferromagnetic background of the system, and that turns actually out to be an extremely difficult problem. So that's something we hope we'll be able to solve with these new quantum machines. It's a problem that some of the greatest minds in theoretical physics have worked on. Here Charlie Kane, Patrick Lee, and Nick Reed, which studied this Gedanken experiment. You know, you cannot do this experiment in a real solid, put a single hole into such a antiferromagnetic environment, but with these systems we can actually do that. So here's actually what we see. This is like this impurity that we place in the lattice that's mobile, and now we can see from these plots how the environment around this impurity is distorted by having the impurity there. And actually we can see there's actually quite a severe distortion in the proximity of this impurity, and this is for us very exciting because it really allows us to get a first microscopic glimpse into what happens when you put these impurities into these special kind of magnets and learn how they modify their vicinity, how they modify their surrounding, how they move completely differently through this antiferromagnet, and that's kind of the first model-independent characterization of such quasi-particles, as we call them in physics, and the first snapshot of individual quasi-particles occurring in these systems. And that's already something we have really trouble calculating, for example, on these supercomputers. So this is really where these systems are offering us answers to problems that we cannot solve today. One final topic I want to talk about before I finish is this thing that connects maybe even more to all of us, and that's the clocks, okay? So you say, well, clocks, why is that important? Well, remember, you know, I have my running watch. Each time I turn on my running watch, it connects to a very good clock in space, an atomic clock in space that sends timing signals, actually from several satellites of the GPS or GLONASS or satellites that send timing signals to my watch so I know my position. I need to receive 3 of those satellite signals, then I can locate my position in space. And so knowing clocks, building better clocks, has immediate implications for navigation. That has been through humankind always the case, and that's still today the case. So we really want to build better clocks. Okay, so to have better navigation in geodesy, to have also for astronomy better capabilities of synchronizing telescopes across different continents with each other to increase the resolution of those, and maybe also to realize fundamental tests of physics to really see whether our constants, fundamental constants we have in physics, really are constants or whether they're actually drifting over time with a very, very tiny rate. So what is a clock? I don't know if you asked yourself that, maybe not. I mean, it's the thing you have on your arm, right? I mean, it's the thing you look on, but what is it actually? Well, for a physicist, a clock is a very simple thing. It's something which has a periodic motion. This could be a pendulum that oscillates back and forth. That doesn't make a clock yet. Then you need also a counter, okay, that counts those oscillations of that periodic thing. And then we can say, okay, let's have this mechanical pendulum, and let's just define the second as 5 oscillations of this pendulum. That's what we could do. We could say 1 second is defined as 5 oscillations of that pendulum. And that's actually what is done. We're just not using mechanical pendula anymore. Those are not good because you can imagine, a mechanical thing, if the temperature changes, the length of the wire is not the same, then this thing will have different frequencies. So we don't do that. So we actually do that today by atomic clocks. And it turns out that today actually the best atomic clocks, the best clocks you can build are built by holding those atoms in these optical lattices that I introduced to you before. So what is the pendulum here? The pendulum is actually the electron cloud of an individual atom oscillating back and forth. So we can set this electron cloud into motion, so it starts to oscillate. And it oscillates very, very nicely because by keeping the atoms separate from each other, we can avoid them bumping into each other and perturbing this collision. So they can really nicely oscillate back and forth without being perturbed by all the other atoms. So that's why we like these lattices. And it turns out these are fantastic clocks, and probably the next generation of definition of the second will be based on such atoms in these clocks. Just to give you an idea, these are clocks that basically, if we would have started them at the beginning of the universe, the Big Bang, 50 billion years ago, they would be just off today by 1 second. Okay? These are clocks that are so good that they can measure also relativistic effects. For example, if you run the clock here, or only a few centimeters below, we know from relativity that should change the rate at which this clock goes. And actually, you can measure that. So you can start, because of this fantastic precision you have with these clocks, you can also look at other fundamental physics effects with them and study them with these. You can use them to map out the geodetic surface of the Earth and many, many more things. So this improved precision that we get here, seemingly, abstract thing, leads to immediate applications to many, many degrees across fields, across science. All right, I think I've come to the end of my talk. Go on, I hope I'm in time. And I just hope I convinced you that these are exciting, objects we're studying. These are exciting, interesting times to study these artificial quantum systems for many, many fundamental physics reasons, for application reasons also. We hope we can apply these quantum systems, as you'll hear tomorrow, for quantum computing to many other applications. This we'll have to see. But it's certainly very, very exciting to have this at hand and to be able to make use of these new observation techniques. So finally, I want to highlight the people who really did the work. It's like, students like you will become probably, maybe in Chalmers, maybe somewhere else, who do the work with us in the lab, and they did a fantastic work. So the Polaron work I talked about, this was Yannis, this is Yannis' PhD thesis. Jaya is a senior PhD student, and Dominic and Sarah are the new PhD students, and Mim and Guillaume are postdocs, and the whole team was led by Christian Groß. And the final team, what I want to show you for the quantum gas microscopes, this is David, new PhD student, Tony, a senior PhD student, June, postdoc, and Simon, also senior PhD student. So with all of those fantastic people, this wouldn't work. This we need fantastic people who are excited about doing these kind of experiments with us in our labs and enjoying, the quantum fun we can have with quantum physics. So with that, I leave you with this nice picture from Munich, and thank you very much for your attention.
So we're now going to have a very interesting exercise, right? Very soon, Professor Alexia Ofev from Grenoble will be coming up here. Right. So, Professor Ofev is from Grenoble, and she's a senior researcher there. Actually, I didn't know about the reading. I found she has a bachelor in philosophy, which kind of makes her recent career then understandable, because she's very, very interested in very fundamental issues these days about the inner workings of quantum mechanics. So she actually did a PhD with the famous Nobel laureate Serge Haroche in Paris, who is actually got his prize more or less for these atomic-like clocks that you saw a description at the end. So, Professor Ofev, are you connected?
Yes.
Oh,
I'm
very,
here.
very nice. So, please welcome. I just introduced you, so I think you can actually start when you like. I should say that the title of your talk is The Energetic Side of Quantum Noise. And in the presentation there, in the abstract, you also mentioned the Maxwell's demon, right?
Yes.
So that's a very interesting little animal, and to understand that one really is a bit of the fundamental issues. And to do it in quantum mechanical way is particularly interesting, because the devil is in the details. So we'll see. Please go ahead and start your presentation.
Okay, thank you very much. So now I'm going to share my screen so that you can see the slide that I've prepared for the conference. Can you hear me properly?
Fine.
You can hear me properly. I don't need to speak louder. Great. So yeah, first of all, sorry to be here just by video conference. Actually, it's kind of a mess today in France. People are striking for the retirement plan, and I preferred avoiding facing this. So I thank you very much for allowing me to give this talk by video conference. So regarding the title, I changed a little bit because the former one was a bit too specific, I guess. So I went to something much broader, which is quantum thermodynamics, basically. And I'm going to try to drive you through this very new field that mixes a bit of quantum physics and a bit of thermodynamics. And after a kind of long presentation, I will go to some very puzzling things we can imagine with this new field, which are new kinds of engines that work just because we look at them, so because we measure them. So. And the second thing that I will consider, which is right in the scope of this conference, is how we can use quantum thermodynamics to have an idea of the energy we need to run a quantum computer. So, yes. Yeah. So actually, this is the outline of the talk that I've just praised. And now, so here is the broad introduction. So when you think about thermodynamics, what you usually think about is the 19th century, right? And the goal of thermodynamics is basically to design engines. So you imagine a source of heat, just like you open your oven in your kitchen, and you feel there is energy in there because the molecules of air are running faster, basically. And you want to use this energy, which is under a disorganized form. You want to extract some good things from it, for instance, to run an engine or whatever, make a train move on. Or so this is actually the scenery I've drawn on the top of the slide. You have what we call heat baths, and these heat baths contain heat, and you want to use some system, some working substance to convert this heat into something good and useful, which is work that you will use to make things move on, for instance. Okay. This is the first law of thermodynamics, basically, that you are going to use it. And this is constrained by another law, which is very important, which is the fact that, which is the second law of thermodynamics, which gives an idea of irreversible phenomena. To be concrete, this second law of thermodynamics, one of the way we can phrase it is that you cannot extract work cyclically from a single hot source. Basically, to make an engine, a train move on, you will need both a hot bath and a cold bath. And to understand this, I've pictured a Carnot engine at the bottom of the slide, where you can see how we can actually convert heat into work. You imagine that you have a gas that contains a lot of particles, and this gas is compressed, for instance, on the left of the chamber that you see. And you couple this gas to a source of heat that gives a given temperature, and actually the gas will expand. And while it expands, it can be used to lift a weight, for instance, which is good work. But now, once the gas has expanded, it occupies all the chamber. So you cannot use it anymore to lift weights. So you need to compress it again, basically to reset the engine. And this reset actually costs work, because now you need to compress the gas again, okay? And this compression, so that you don't pay too much work, you want to do it while the gas is connected to a cold source instead of a hot source. So that's the reason why you need two gases, two temperatures to operate your engine. Okay, I'm insisting a bit because actually these pictures, if you build this in your mind, they contain lots of physics when you go in the microscopic realm and in the quantum realm. And for instance, there is a guy, also in the 19th, that you probably know, which is called Maxwell, who designed a paradox around the story of the Carnot engine, which is the following. Imagine that there is a demon, an intelligent being, that is able to know the position of the particles and to sort them. Then, actually, the reset of your engine, you can do it without compressing the gas. You can do it at no work cost. And it seems that using information, using an intelligent being, allows you to run an engine with a single hot source cyclically. So it seems to violate the second law of thermodynamics. And so that's the Maxwell's demon paradox. And this is basically the Maxwell demon engine that you see here. And we had to wait like 1 century to see this paradox solved and Maxwell demon exercised. And the idea is actually the following. It's that information is physical. So basically, it's not some sort of immaterial concept that you can use without paying, actually. There is no free lunch. If you use information, if you process information, you will have to follow the law of thermodynamics as well. And, okay, to understand this, the fact that information is physical, it's very convenient to pick up Carnot engine again, but instead of thinking about a Carnot engine with a gas of particles that contain lots and lots of particles, just imagine now that your gas has just one particle, okay? And this particle can be on the right or on the left of the chamber. With this, you can easily understand that right or left can be used to encode information. It can use to encode what we call 1 bit of information. And here you have basically the model of 1 bit of memory, 0 and 1 for right and left. So now that you have this in mind, let's think about the Carnot engine again. The Carnot engine, if you look at the expansion of this some sort of ideal gas, you are going to be able to extract work, fine. But you can understand this like this. In the beginning of the process, you know that your particle is on the left. In the end of the process, you don't know anymore where it is, but it can be on the right or on the left. So you basically lost 1 bit of information on your particle, but at the same time, you've extracted work. So you have converted 1 bit of information into some elementary work. This ideal engine, it's called the Szilard engine. And on the other hand, the compression, you can understand it like this. In the beginning of the process, your particle can be on the right or on the left. In the end of the process, you have compressed it on the left. So now you know that your particle is on the left and you have resetted your memory. And actually this costs an elementary work because you've compressed it. And this is what we call Landauer's erasure work. This Landauer's erasure work, it's a fundamental bound to process information in classical computers, and this is some order of magnitude that we will face at some point when we keep on playing with efficient computers. And obviously this exercises the Maxwell demon, okay? So now that we have this, I want to say that actually these Gedanken experiments are not Gedanken experiments anymore because they have been implemented. Third Szilard engine has been implemented in Japan in collaboration with Masahito Ueda, and the first readout of Landauer's erasure work was implemented in Lyon. So this is real physics that I'm talking about. These quantities can be measured. All right, so now to keep on moving in history, what you may have noticed is that I've talked about thermodynamics using systems which are not systems that contain large amount of particles anymore. I'm not talking about a gas. I'm talking about ideal systems that typically have 2 microstates, okay? And so I've drastically miniaturized the size of the working substance. And this is actually the scenery for a new era of thermodynamics, which is called stochastic thermodynamics, where we had to redefine what is heat and what is her work, but at these very, very little scales. So for instance, imagine that I have my bit that is pictured here, my 0 and my 1, and this bit is coupled to a heat bath. Just like before, I had my gas that was coupled to some well-defined temperature reservoir. What happens? The effect of the bath on my bit is to let my bit fluctuate, okay? My bit won't stay quiet. It will undergo passages from 0 to 1, from 1 to 0 at a very fast scales. These are fluctuations, this is noise. And these fluctuations, actually they carry energy. My particle is agitated, so this has energy. This is basically heat at this small scale. Heat equals fluctuations. On the other hand, I can try to control my bit. I can try to implement a protocol on my bit. For instance, I can imagine that my bit, there is a difference of energy between a 0 and a 1, and I can change this energy. To do this, I'm going to perform work on my system. And this is basically how we define heat and work at the microscopic scale, okay? So now, how can we think about an engine? What is an engine at this scale? An engine is nothing but a device that allows me to extract work from thermal fluctuations. It allows to rectify the fluctuations. And with this, I can design nano engine and information engines. On the other hand, these fluctuations, they are also responsible for irreversibility. And the way to understand it, it's very simple. You can try to implement a protocol on your small system. And so you're going to bring your system from one state to another state in a very well-controlled manner. And then you want to bring it back to its initial state. That's one operational definition of reversibility. Now imagine that this actually system fluctuates because of the bath. You won't be able to bring it back to the initial state because of the random perturbations that are imposed by the temperature. So you see that actually irreversibility here is tightly connected to the fact that I don't control my system entirely because my system is subjected to random perturbations. I'm insisting on that because this really gives another picture of thermodynamics. Thermodynamics is based on randomness at this scale. And you can perfectly imagine that you will be able to build a consistent version of thermodynamics if there is some source of randomness somewhere, okay? And you see me coming. Right now, I'm telling you about randomness that is here because of temperature, but there are other sources of randomness in nature, and typically the randomness that you find in quantum mechanics. And this will be on that we are going to build quantum thermodynamics, okay? So, well, this brings me basically to quantum thermodynamics. And so how did we introduce quantum thermodynamics first? we picked up the scenery that I was describing here with a small system that is subjected to a controlling entity and subjected to thermal fluctuations. And we said, okay, actually, these guys, they pertain to a Hilbert space and they follow quantum rules. And for instance, my bit now can be a qubit. So I'm going to encode information, not classical information, but quantum information. So I guess you're going to hear about this at length during these 2 days. So I'm just giving you a small flavor of what quantum information is. Quantum bits, qubits, they are the building blocks of quantum technologies. And the big promises of quantum information technologies is that we are going to compute faster than in a classical computer, and that we are going to communicate in a much safer way than in the classical realm. Why? So really in a nutshell, here is what we call the Bloch sphere. So the Bloch sphere is nothing but a geometric way to represent any kind of quantum state that my qubit can have. So you find the 0 and the 1, which are the two states, the two states of the computational basis, And you can build any kind of state that is written, so I'm not going to read the formula, it's a bit boring. But what you can see is that when my qubit is prepared in this state, which I call psi theta, we say that it's, this qubit is in a coherent superposition of zeros and one, where theta and phi, they are what we call quantum phases. And we cannot understand this state as being simply, oh, my qubit is either in 0 or 1. It's really in both states at the same time, okay? And this gives rise to interference behaviors. And these interference behaviors are really at the heart of the power of quantum information processing. It allows to build, to use quantum parallelism, for instance, compute at the same time many values of a given function, etc. So these coherent superpositions, they are really in the heart of the power of quantum technologies. Now, what happens when I measure this state? So here you see, I still have my Bloch sphere, and I measure this psi theta. Basically, I ask my bit, are you in 0 or 1 state? And then I get two random outcomes, 0 or 1. And these random outcomes, this is quantum randomness that I'm talking about here. It's not possible to foresee before. No one can know in which state my qubit will be projected in the end. And this actually brings two possible quantum trajectories. Either my qubit goes from psi theta to 0, or either my qubit goes from psi theta to 1. This is called quantum trajectory. While I'm measuring, my qubit evolves by what we call a quantum jump or a collapse. And this quantum jump, it's violent. You see, I jump from one state to the other. And this is because of the fact that basically one way of stating this is that quantum measurement perturbs. And this perturbation, just to close the loop with what I was saying before, it's the mere reason why information can be propagated safely. Because if there is a spy that tries to observe the state of my qubit, it will be immediately detectable. So that's why we can communicate safely. And last point about quantum measurement, which is extremely important as well. Once the qubit is in 1 or in 0, it cannot come back into psi theta. I cannot know where I'm coming from. So quantum measurement is irreversible. And this irreversibility, as you can see, like I was saying before, it's related to the fact that there is some sort of randomness in there. And here in that case, it is quantum randomness. Okay, so with these notions, actually, there are many ways to do quantum thermodynamics, basically, and there are many very nice questions that you can ask. For instance, I told you about the Carnot engine. The Carnot engine has a well-defined efficiency, and it has well-known performances. But then, can we use the fact that my qubit can have coherences to outperform classical engines? Like I was saying, what is the energetic cost of quantum computation? What is the specificity of quantum Maxwell demon? Are they better or worse than classical Maxwell demon? How can we count? How can we measure quantum irreversibility? So all these kind of questions are currently studied in this new field of quantum thermodynamics. And now, now what I'm going I'm going to focus on a specific lead that I have chosen to follow to do my research, which is the following. Let's consider this scenery of quantum thermodynamics. So you see you have qubits or quantum systems that undergo the exchange of heat on the one hand, and that are controlled by some controlling entity on the other hand. As you can see in the picture, there are two sources of randomness now. There is the thermal randomness that we know from classical thermodynamics, and there is also the quantum randomness that comes from the fact that my measurements, they have random outcomes. The two dices here are pretty different. They have completely different nature. One is ontologic, if you like, and the other one is epistemic. I'm just squeezing here a few words of philosophy because know that there is a bit of quantum foundations that we can also do with this. Okay, so once we have this, actually we can ask, okay, it's a bit complicated, all this. So I want to restrict myself to study the concepts of thermodynamics if my source of randomness is only quantum. So now I'm going, instead of using a hot source, I'm going to use projective quantum measurement as a source of randomness, as a source of irreversibility, and as we are going to see, as a source of energy as well. And the small paper in the bottom of the slide is, if you are interested in quantum foundations, these questions are discussed. Okay, so what are the motivations here? I want to know if now I will be able to extract work from quantum measurement only. So are there engines that are driven by quantum measurement on the one hand? And on the other hand, is there quantum irreversibility that is induced by quantum measurement? And how does this quantum irreversibility put bounds on work extraction and on the performances of the engine I'm going to try to design? Okay, so that's the goal. And in the end, well, that was the third part of my talk. I hope I can reach that because I see that I'm talking slowly. But anyway, the important thing is that this idea goes through the Visio and your minds. Okay, so before I present you the engine, I just want to put a bit of definition on this. So here is the scenery to which I am restricting the problem. I have a quantum system S. I'm driving this system with a Hamiltonian, and at discrete times, I'm measuring this system in projective manner. So basically, this is what you learn when you learn quantum mechanics at your first lecture, basically, or say second lecture. Okay, so with this, here what's going on? If I start from a well-defined state of my system, I let it evolve with the Hamiltonian, and I read the measurement outcomes at discrete times, I can build a stochastic trajectory of pure quantum state, just like I told you before. I do have a well-defined state of my system at each time I want. So here, T1, T2, and T3 are the moment where I measure. Between T1 and T2, my system evolves continuously with its Hamiltonian. And at each time, T1, T2, and T3, you see the quantum jumps that come from the fact that I have measured, all right? So what is work and what is heat in there? Well, it's very simple. Work is exchanged while my system is moving continuously, and heat, quantum heat, is exchanged while I'm measuring. And this quantum heat, this energy fluctuation, it's important to realize that it has no classical equivalent. It doesn't come from a hot source. It's really coming from the fact that my measurement perturbs, and if it perturbs the state, and if it perturbs the state, it perturbs the energy. Okay, so this is quantum heat. So here I picked up, so that you understand better what quantum heat is and how magical it can be, I picked up my block sphere again, and I do the following Gedanken experiment. I prepare my qubit in the ground state, 0, and I measure it. So instead of measuring it in 0 or 1, I measure it in these two states here, plus or minus. What you must realize looking at the block sphere here is that the higher the states are in the Bloch sphere, the more energy they contain, okay? So 1 contains more energy than 0, and plus and minus contain more energy than 0, okay? So now, starting from 0, I'm asking my system, are you plus or are you minus? And what you can see is that applying the laws of thermodynamics tell me that there are 2 possible outcomes, plus or minus. And in the end, my system will be projected on plus or minus, meaning that energetically speaking, I start from a state which contains no energy, and I end up in states that contain energy. So my measurement has provided energy on average to my system, okay? And now the whole point of this quantum heat is to see if I can use this quantum heat to design an engine, just like Carnot designed an engine by using cold bath and hot bath, okay? So actually there are, I have still, I guess, 7 minutes. Am I right, or a bit more? I don't, because I still have a few slides, so I don't know if Peter can send me an email to tell me how many minutes I have. That would be helpful, so that I can adapt my rhythm and my elocution. Thank you very much. So now, actually, I'm aborting the second part of the talk, which are the applications of this concept. And I want to show you first that it is possible to run an engine just by looking at it, and then to have a few ideas about the energetic cost of a quantum computer. So first of all, the engine. So here is the strategy. Like I said in the introduction, engines, they are nothing but these devices that allow to extract work from thermal fluctuations. And now I want to play the same game if the thermal fluctuations that come from hot sources are replaced by quantum fluctuations that come from my measurement, my quantum measurement, okay? So to do this, actually it is possible, and I'm going to tell you the basic mechanism of the engine that I had in mind, and I don't think I will have time to tell you the math, but I'm just giving you the picture. So what is my working substance? It is still my qubit. So a qubit, I can use a 2-level atom with a ground state and an excited state. Now, if I send on my qubit some resonant light, so basically photons which have the same frequency as my qubit transition, then I'm going to launch what we call in jargon Rabi oscillations. Basically, my qubit will change its state. It will go cyclically from G, the ground state, to the excited state, and back to the ground state, going through the state plus and minus that you see on the picture. So this again is called a Rabi oscillation. And now there are 2 regimes basically. While my qubit is going from plus to G, then it sees actually its energy decreasing, meaning that my qubit is providing energy, it's giving photons to the driving light. And on the other hand, while my qubit is going from G to E, it's actually absorbing photons from the driving light. Now, my purpose is to design an engine. So actually, I want my qubit to keep providing energy to my driving light. So how can I proceed? Actually, the way I proceed is simply to enforce my qubit to stay in the plus state. And to enforce my qubit to stay in the plus state, the thing that I can do is simply measure my qubit at regular intervals of time and ask him, are you in plus or in minus? And if the guy is in minus, I apply what is called a feedback to enforce it to stay in the state plus. And that's the principle of this machine. And actually, you can really see it as a Maxwell demon, because when I perform my measurement, I'm not sure what I'm going to find. Is it plus or is it minus? But then I can use my knowledge on the system state to enforce it to give energy to the driving light. The big difference with respect to usual Maxwell's demon, the one that, for instance, Maxwell's design in the 19th is that the energy that is running my engine now is not extracted from any hot source. As you can see in the picture of the engine, there is no hot source. It's really coming from the measurement itself. So this is why we call this measurement-driven engine. All right. So here are the steps of the machine. And actually, since I'm running out of time, I won't go through the steps, but I can use these slides to answer questions later on if you like. The important thing is that you get the main idea, which is I can use an engine just by looking at it, which is the motto of this part of the talk. Okay. So there were quite a few slides. Just to tell you that also I'm still waiting to see the experiment done. So I'm currently lobbying a few experimentalists to see this coming, because running an engine just by looking at it is something that is very nice and would be nice to be observed experimentally. Are different setups that we had thought about, like superconducting qubits or semiconducting quantum dots, but I won't enter into details. And so this will be kind of a concluding part, which is thermodynamics can be used to design machine to extract energy from fluctuations, but it can also be used to compute energetic costs. And so here is here are the basic concepts that we can think about. We need to go back actually to thermodynamics of classical computing first. So here is a picture of classical computer. And the idea of a classical computer is that you process data inside. So inside your computer, you will find what we call gates, okay? And these gates are actually, in a classical computer, logically irreversible. By what do I mean by this? I mean that I put here the example of a NAND gate. You see that you enter information that is encoded on 2 bits, 0001, 1011, and you end up with a result that is encoded on 1 bit, 1001. So you see that you've lost 1 bit of information on the way. And if you lose information, it actually causes heat dissipation. Irreversibility causes heat dissipation. This is one of the major points of thermodynamics. And this gives us actually the lower bound, the lower energetic bound of classical computing. Basically, by using Landauer's limit, the one I told you in the beginning of this talk, we can estimate that each lost bit corresponds to 10 to the minus 21 joule, all right? While the current consumption of a gate inside the computer that I'm using right now, it's 10 to the power minus 17. So you see, we are basically 4 orders of magnitudes above. And if I simply use current data to project the energetic cost of a gate, around 2028, we should reach Landauer's bound. Okay? So now, what happens for quantum computing? If you are a bit in the field, you know that energy and quantum computing, people don't talk about this that much. While there is an extreme big advantage of quantum computers, it's that they are reversible. You can perfectly run, in the absence of noise, a quantum computation in a reversible manner. And the reason for this is that the gates that we use in a quantum computer, they are themselves reversible. So here I put the CNOT gate, for instance. As you can see, you enter 2 qubits and you end up with 2 qubits. And the operation that we do to process these 2 qubits, they can be reversed. So basically, in the ideal world, we could perfectly think about running a quantum algorithm without dissipating heat, okay? So that's one thing, but then does it mean that we could run a quantum computer purely at no work cost? So obviously no. And but the cost that we are going to have, they actually come from the gate that we perform to implement our logical operations. So here is again our favorite system, the bit. And as you can see, this bit can be perturbed by the environment. So there are various noise and perturbation channels that we can think about. But on the other hand, I'm trying again to control my qubit by performing, for instance, radio oscillation and implementing gates. And actually these gates, it costs energy to perform them. And if I constrain this energy, what we can see is that it induces, again, noise. So I'm finishing now because I started to hear the audience. So I guess I'm at the end of my talk, but I can just guess because I don't see any sign of I should stop. So I'm moving on.
Alexia,
yes,
Alexia, can you hear me?
I can hear you.
Can you round off in a minute?
I'm concluding now.
Super.
I'm almost there.
Okay.
So I was just finishing on the orders of magnitudes that we could expect for physical quantum gates, but I'm not going to comment because I'm going to conclude. The only question I wanted to address here, and the one that we are working on, is will we need a nuclear plant to run a quantum computer? And so here is my conclusion. So I hope that from remote, I could give you the feeling that quantum thermodynamics is a very interesting and transverse field that goes from very deep fundamental physics, like the quantum arrow of time, quantum information as a resource, what is the deep meaning of randomness, to very practical and essential tools to assess the energetic cost of future quantum technologies. Regarding the outlooks, so the topics that I'm investigating right now, it's always about quantum engines that will be fueled with entanglement, quantum coherence, and many-body system, thermodynamics of logical gates and error correction, and also is quantum thermodynamics a new way, a new path to decipher between the different interpretations of quantum physics and convincing experimentalists to do these marvelous experiments. A picture of the people I'm lucky enough to work with in particular the Grenoble group with the students that work on the topics I've mentioned. And I just want to advertise for a conference on quantum thermodynamics that will take place in Barcelona in April for those who may be interested. I thank you for your attention and well, ready to answer questions after the coffee break. Thanks.
Thank you very much. Ska vi korta av pausen? Nej? Okay, so thank you very, very much, Alexia. That was a great talk. I should, because some of you guys over there may be wondering why we are doing this teletransmission from Paris. It's because, as you know, the French are experts at faire la grève, to have, to strike, and they don't like the ways that Macron want to change their pensions. So there is big hullabaloo down in Paris and all of France. So that's why we have to do it this way. So we will be talking a little bit about the discussion session right now, but you other people are invited to take a break and go and have coffee, and the coffee is on this level and also on the lower level, so you don't have to line up here. So back at 10, right? 11, yeah. Right, thank you very much. Bon, tu peux m'avoir, mais...
Oui?
Moi, je suis Göran Vendin de MC2. And I think we have met at times, but I'm not sure. Anyway, we will now have a discussion of how to handle the discussion. So we'll be talking with Emmanuel Bloch and so on, how to do things. You hear me, right?
Yes, I hear you, but I can't see you, which is a bit puzzling.
Bon, tu es à Grenoble maintenant? I think so.
So how
Honestly, I don't know. Maybe you cannot tell.
because they recommended that I check before.
Yeah.
Microphone and the camera right now. Yeah. So you want us to talk on the phone?
In the quantum world, particles possess both particle and wave-like characteristics.
So take your seats quickly, please, as we are about to begin the Q&A session. So I will tell you how it's organized. We have 2 microphones here. So if you have a question for one of the speakers, you step up and stand in a queue behind one of the microphones. Please direct your question so we know this question is for Professor X, because we will have one sitting here and one will be on the screen there, so it's it has to be clear who you're asking. And try to be brief when you ask your question, because there will be plenty of people who want to ask questions. So, with that, it's just, who wants to go first? Just step up to the microphone, and I will hand over to Göran now.
Thank you. So please take your chair, and I'll take a more modest chair down here. So, okay, guys, you are invited to approach the mics and pose your questions. You come down, you line up, and you actually talk to these microphones in front here, right? And don't be shy. I mean, it's nice to have long lines here, right? And please state your name and where you're from, and then ask your question.
My name is Tim. Oh, let's see. My name is Tim. I'm from Lars Kag in Kalmar, and I have a question for Emmanuel Bloch. I believe you said you upscale matter to be able to measure and study it. I was wondering how this is done.
So you mean the measurements to study matter, or sorry, I didn't. The echo was a bit. Can you just repeat the question?
I believe you said you upscale matter.
We upscale matter. Yes. How that's done? Well, because basically, okay, we can't just pull and stretch a real material to make distances 10,000 times bigger, because you know exactly what happens. It'll break, right? I mean, if you try to increase the distances between the atoms, it will just snap at some point and break. So we can't do it in real materials. So we have to go to these drastically different routes of building artificial materials, where basically we control the scale of how big things are, how distances between different, let's say, positions are, and we do that through these optical patterns. So for us, the optical pattern creates the potential landscape in which the atoms move, and basically we control that potential landscape by just interfering the laser beams from the outside. So something in a material, normally the material does itself create this landscape, but here really this is created from us, from the outside. And that's why we can do things, so we can scale things up by a factor of 10,000 and not have to worry about that. Yeah? That's a good question, yeah.
So you create a sort of simulation to study it?
Exactly. That's what we also speak of, quantum simulations, quantum emulations, to study these real material, behavior of real materials in these model systems. Absolutely. Mm-hmm.
Thank you.
You're welcome. Thank you.
Hello, I'm Helen from Lund, and I would like to direct my question to Professor I can't pronounce names, sorry. So, yeah, sorry. You were speaking about this thermal randomness, and I wonder, more specifically, what it actually is and where it comes from.
Where does thermal randomness come from? Yeah. Is that your question?
Yeah.
Okay, so there are many ways to answer that question. So the idea first, the basic idea is that if you have a thermal source, then you induce fluctuations in your small system, right? These fluctuations, this is noise. And it means that at any time you cannot really predict where your system will be. So it's random. Now, why do I claim that that thermal randomness, for instance, is different from quantum randomness? So basically, the idea is that it's linked to our degree of description. If you were able to model the thermal bath a thermal bath, it's also a physical device, right? It's also lots of particles that move around and create some temperature. So if I was able to model all the particles that constitute the bath, plus the system that undergoes the fluctuations, then I wouldn't really talk about randomness anymore, because I would be able to describe the whole system and its whole evolution as a function of time. So everything could be predictable, okay? While if we are in the case of quantum randomness, for instance, like I said, there is no way I can complete the system so that the evolution does not become unpredictable. That's why the two sources of randomness are so different.
So would you say that thermal randomness is technically predictable if you could like calculate every particle's path?
I would say, so I'm not sure I fully heard the question, but I would say that, again, if we were in this ideal situation where all positions of the particle were knowable and we model everything, then there wouldn't be any thermal randomness, yes.
Okay, thank you.
My name is Loba, I'm from Gothenburg, and I have a question for Emmanuel Bloch. You mentioned briefly about negative temperatures and anti-friction, and I was just wondering about the correlation between temperature and friction and anti-friction.
Yeah, so this is a special property that these gases have. That so normally, you know, when you have a normal gas like air surrounding us, and we send something through, or let's say a fluid, and you send a ball through that fluid, there's friction, and you basically generate entropy. And now the special way, well, entropy, I should explain, is a measure how we kind of describe the amount of disorder in the system. So we like to use that in physics and statistical physics. Now, these negative temperature systems, they have a very special feature that their kind of entropy can increase when we lower the energy. Typically, it's something we don't experience. So let me explain why it's so strange. Usually, if you heat water, you need energy. You need to put in energy to heat water, and that increases the amount of disorder. The particles are moving more, but this gas is the opposite. And now if you send through this gas, actually an impurity, what you actually expect is not that it slows down or a ball, but actually that it speeds up. So it has really strange properties, and that we're not used to from normal. It's also a gas which we actually need to perform work on when we want to expand it. For example, usually, you know, when we want to compress a gas, we need to put work from the outside to compress the gas. It's a little bit actually connected to what Alexia was saying in her talk. But in this negative temperature system, it's also a bit weird because there you actually have to perform work when you want to expand it. So it's actually the opposite. So a lot of the things we know from thermodynamics and statistical physics are quite the opposite in these negative temperature systems. So they're really very peculiar systems from a thermodynamic point of view.
Okay, but so if you were to throw a ball through this negative temperature gas, what would that mean for the entropy of the system?
Well, the overall entropy always increases, but actually in this case, actually the ball would accelerate. So entropy would increase, but the medium would give energy to the ball, so the ball would actually increase in velocity.
Thank you.
Hello, my name is Alexandra, and I'm from Lidköping. And I have two questions for you, Professor, if that is okay.
Sure.
So, do you want to start with the easy one or a more nebulous one?
Please, with the easy one, yes.
Okay. Is it possible, you spoke about these, kind of cages for atoms. Mm-hmm. Is it possible to create such a cage with only a single beam of light?
Oh yeah, sure. That's what these tweezers were, what I explained, what actually a lot of my colleagues are doing. You just take a laser beam, send it through a lens, focus it, so it becomes really focused at some point, and in the focus point, where the laser beam is very small, you can actually trap individual atoms.
Okay, so it's not very, specific. You can't create something great, so some kind of advanced structure with a single beam of light.
Well, you could. Well, what they're doing, that I showed you. Did you remember the Eiffel Tower?
Yes.
So that was really. So that were multiple arrays of laser beams. So each atom was trapped in one laser beam, Okay, and but now having many laser beams, many arrangement, you can actually have very complex structures. But just putting an atom wherever you want. You just shine a laser beam where you want to put an atom.
Okay. The second question is about these arbitrary light patterns, the clocks, you know. So you said they kind of moved at both sides, but only horizontally. Do they move adjacently? Sorry,
I didn't understand the question. So can you repeat again?
No,
it's just acoustic
that,
also. Sorry.
Okay. You had a pattern up on the screen.
The pattern. Mm-hmm.
Yeah, and it was a clock, you said, and there were atoms that moved at different sides. So one moved left and one moved right, and you couldn't really predict which one would move the fastest. Mm-hmm. But do they only move to side, or do they move like up and down too?
Okay, now you are talking about the quantum horse race, yes?
Yes.
My quantum horse race. Yes, we restricted the movement such that they could only move in one line. They cannot move up and down. We do that. You want to know how we do that? So we basically just have another laser beam which squeezes them in the vertical direction, so they basically cannot escape in the vertical direction. So we really can tell them to move only in one direction, left or right. Yeah, they're allowed to do that. But we only know who won the race, you know, when we observe. So it's like a strange race. You're not allowed to look, because when you look, you destroy the race. You immediately get the outcome of the race. So you are not allowed to look during this race. Mm-hmm. Those are the rules in quantum for the quantum race.
Thank you.
Hello, my name is Axel, and I come from Polhemsgymnasiet in Gothenburg. And I have a question about this negative temperature for your block. So the definition of 0 Kelvin is that all the molecules and particles are standing like still. And so how are these gases able to go below that?
Yeah, so good question. So usually you think of temperature associated with energy content of a system, but that's not how in physics we fundamentally define temperature. So temperature for us is basically the derivative, 1 over temperature, 1 over T, in thermodynamics, is the derivative of entropy versus energy. So remember, entropy was this quantity which describes the amount of disorder in the system. And so if you make the derivative of entropy versus energy, then typically it's positive for normal gases, because when you heat up a material, you increase the disorder. Think again of your kettle of water. When you heat it up, particles start to move faster, so things are getting more disordered. Now, but there's nothing wrong. We can design systems where actually, when we add energy to them, they become more ordered. So that's strange, because we don't know that typically. But we know in the quantum world we can have such situations, and we can have it also for free gases of atoms. So this is a gas like that. And if you think about it from this fundamental point of view definition, then actually we can make a gas where we add energy, it decreases entropy, and then that derivative would be negative, and now we are at negative absolute temperature.
All right, cool.
Thank you.
Hey, I'm Timo. I'm a guest master student here from Germany, and I was wondering also about your quantum horse races. In particular, I know that there are like quantum random walks, so could you emulate these graphs on your horse race track?
Sure, that is a continuous time quantum random walk. That is a quantum random walk. It's just performed in continuous time. We don't have discrete steps. Usually, so this is like more for the experts. You're an expert, so usually you have these coins that you toss in a discrete quantum walk. Here it's basically, if you want to call it in complex words, a continuous time quantum walk. That's what it is.
And can you engineer like a specific graph you walk on, or?
You could also do that by then really doing it all in discrete versions and then engineering the amplitudes and phases for each step that you do. Yes, you can do that. I mean, there's been nice experiments in the group of Dieter Meschle in Bonn, for example, that have done things like that. Yes,
right.
Absolutely.
My name is Gijs, and I'm from Strängnäs. My question is to Professor Bloch. You were speaking about the different laser configurations with the for trapping the atoms, and one of them involved two blocks where the atoms would flow from one block to the other. Is it possible to observe these blocks to create bits of it, like bits of information, as in ones and zeros?
Yeah, we can do that, but remember in the quantum world, when we observe, we fundamentally change. This also relates to Alexia's talk. So you're not allowed to, when you look, actually, you're changing the state of the system already. So that's, you can do that, but it will change your experiment that you're doing. Yeah? So if you look, if you count, let's say, then it will change the behavior of your experiment. So fundamentally, if we just want to prepare a certain quantum state and see how it evolves, then we're not allowed to look before the end of the experiment.
Right. No, thank you.
Hello, my name is Anton. I come from Eastern Scania. I had a question for you, Emmanuel Bloch. You talked about single atom impurities in quantum magnets, and I was just wondering where this research could be applicable in like our day and life, and what you could use of this knowledge we gain.
Yeah, so I mean, we believe, okay, well, this relates to the big problem of understanding what we call high TC superconductors. So these are materials which lose all kind of electrical resistance, typically below a certain temperature, superconductivity, and that's the phenomenon of superconductivity. For high temperature superconductors, this happens at higher temperatures, but still we'd love to have that at room temperature, right? I mean, if I could make a conductor which has no resistance and have power delivery over distances without any electrical resistance, that would change our world, you know, in what we can do. So we want to understand these better, these materials, and even the simplest models that people have written down for these materials, we have not been able to solve. I mean, that's frustrating because the models are really simple when I write you down the equations which describe how the particles interact, but we can't solve them. So one key thing that people believe is that we need to understand is this interplay of how do impurities move in this antiferromagnetic background, single ones, but also multiple ones. When you have more of them, can they, you know, form kind of this new superconducting state? So these are exactly questions that we want to answer, and this new microscopic view on the problem gives us a new handle of addressing this problem.
Okay, thank you.
Just a moment. Sorry, I got the permission by the organization to go 60 years back in time to your age and actually just ask one question for Alexia. Are you with me?
I am with you.
You talked about random processes and so on, but you actually talked about quantum randomness, right, as a very fundamental thing. Sure, it's fundamental, but in principle, if you keep all the information, you can actually track the quantum jumps, right? So, I mean, that's what Michel Devoret and co-workers recently did, that actually by properly measuring, the jump is not random, you can actually follow it and you can restore it. Do you have any comments on that?
So the fact that you can observe the jump does not change the fact that it is random. So you can observe the atom jump from E to G and from E to G with great efficiency, but you cannot predict in advance that it will be jump or not.
No, but in principle, the measurement induces the thing, and you can actually track that change if you do it carefully enough, right?
Absolutely.
Okay.
Absolutely. But I don't really see to which extent the fact that I can observe and track is incompatible with the fact that it is random.
Okay, thanks.
It's unpredictable. Just before you can't know it will happen, and after it has happened.
Sure, d'accord.
Voilà.
Hello, I am Gian from Procivitas Växjö, and I have a question for Alexia.
I'm here.
So, you said that you could create this theoretical engine that uses observations to create work, but wouldn't the observation themselves require work since you gain information by them?
That's an excellent question. And actually, this is in the heart of some discussions that are currently taking place in the field of quantum thermodynamics. And indeed, it costs energy to measure. Measurement does not happen for free. So my point in suggesting that we could implement this kind of engine was not to invent a new resource in some sense. It's not something that is useful and we save the planet just like you save the planet by not taking things. It's pretty different. It's more a proof of principle that energy is associated to measurement, and that if I proceed properly, I can extract this energy and convert it into another kind of energy. That was more the purpose of this proposal.
Okay, thank you.
Hi, my name is Nilo. I'm from Borlänge. I have a question to you, Professor Block. I just wondered, when you mentioned your simulation when enlarging a material 10,000 times and then cooling it down to extreme temperatures to compensate for the enlarged scale, is it enough to compensate for by just cooling it down to extreme temperatures, and how accurate can such a simulation be compared with the original state?
Good question. So yeah, the first question is yes, it's enough to cool it down sufficiently, because, as I said, in quantum systems, the only parameter that tells us whether these act like collective quantum states, you know, where these particles interact with each other, is this parameter lambda over d. So if you make the same lambda over d, irrespective if you're in a neutron star with extremely high densities of fermions, for example, of neutrons in the neutron star, in the core of a neutron star, actually we can look at pretty much the same physics with ultra-cold gases at, you know, densities which are 5 orders of magnitude more dilute than the air surrounding us, simply because this parameter is the same. Okay, so that's the first question. And the second question was, I forgot now.
How accurate can such a simulation be compared with the original state?
Well, so first of all, one has to say, of course, that these real materials are super complex things. I mean, they have impurities, they are not they have defects, they're not perfect. Also, they are much more complicated usually than what we can do in the lab. So we first of all try to make a simplified model and to try to capture what we believe is the essence that's going on in this material, and then we try to build this artificial quantum material according to these rules of this simplified model. And we try to make the model more complex and complex to adapt for the more complex things that can occur in a real material. But that's a good question, yeah. But turns out already for a lot of these very simple approximations, we don't have the answer, and that's frustrating somehow, yeah. So we have to try new ways to find that.
Okay, thanks.
Hello, my name is Rishi, and I'm a master's student here at Chalmers. My question is to Professor Block. So you said that you can create gases with negative temperatures, and is it possible to spontaneously switch from, I mean, not spontaneous, I mean, is it possible to, how easy is it to switch from negative temperatures to like real positive, I mean, above 0 Kelvin gases?
Yeah. So that's what we actually do. So we start with a positive temperature gas, and then we do a sudden switch in our system, in our Hamiltonian, so you know what that means, of the system, to suddenly switch it, and that basically creates out of a positive temperature state a negative temperature state. So by doing a very sudden, non-adiabatic switch, we can convert between the two, actually.
And how about the reverse?
Sorry?
How about the reverse switch from...
You can also do the reverse switch. You can also switch back if you do that suddenly, yes.
Okay, and about the atomic clocks using lattices, what is the benefit of using a lattice and not just a single atom to make the oscillations?
Because you want to pick up the beat. You know, you have these oscillating electron clouds, and the more atoms you have, the more signal you basically get, right? And you want to pick up this. If you would just have a single atom and you would have to measure this oscillating electron cloud, it will just give you a very weak signal because it's a single atom. If you have many more atoms, then actually you can have a better signal to noise in technical terms. So your signal improves, so you can pick up this oscillation of the electron cloud much more reliably.
And
because they're all oscillating the same. Remember, we have these atoms, but they're not doing independent things. So we have them sitting in the lattice, and we start the oscillation of the electron cloud all at the same time. So they're all oscillating with the same oscillation. All of them also doing the same thing. But they're just amplifying the signal that we can pick up from them.
And I have another question for Professor of Alexia. Yeah. So you said that in the Rabi oscillations, you can take it to the ground state, and then you can measure it in the X basis, and you can extract and work from that. So could you maybe think of an example where that could be useful?
So again, the usefulness is certainly not the best criterion to evaluate this proposal. It's more a proof of principle again that quantum measurement is another source of energy, basically. And but this is not with this we are going to create engine that will play a revolution. Okay, so the example. You ask how, in a concrete manner, we can implement this measurement in X basis? That's your question?
No, my question is, so if I understood correctly, when you're measuring it, you're supplying your system with some energy, yes. And you're trying to figure out if you can extract back that energy and do something with it.
Yes.
Oh,
yes.
Okay. Yeah, that was it.
That's it. So I'm showing basically that I can control the mechanisms such that the energy that is initially contained in the measurement channel, okay. Which by definition random, I can convert it into some energy like propagating photons that are much more controllable and reusable.
Okay, thank you.
Hello, my name is Herman. I'm from Globala Gymnasiet in Stockholm. My question was for Block. First of all, thank you for your amazing talk. But I was wondering, you said that you could upscale materials to, 10,000 times, I think. Could you do it bigger? Could you do it 100,000? What about a million, a billion? Could you do it millimeter scale, meter scale?
Yeah, good question. So why don't we do that? That's possible, absolutely. I can increase the distances even more. The problem is then they basically just become independent atoms. And somehow I don't want to bring them too far apart because I still want them to interact with each other. I still want them to come in contact with each other, to move at reasonable time scales. You remember we said when we scale up things in quantum mechanics, things slow down? So if I would go to even much larger scales, it would slow down to scales where it would maybe take a year for the atom to move from one place to the next. And that's kind of too slow, right, when we want to do an experiment. So we have to find the optimum, and that's kind of the optimum we place ourselves. Okay.
Yeah, thank you.
Hello, my name is Amanda.
And my is Fabian.
And we're high school students from Ökre Seglande Gymnasieskola, and we have a question for Professor Bloch.
Yes, you said light can move, or atoms can move between the two boxes from a beam of light, but also laser beams can hold an atom in place. Why doesn't the atom move along the laser beam?
So we basically, the shape of the potential we create is basically just given by the intensity distribution of how much light you have at a certain position. And it turns out actually in these cases, the light we use with the special frequency, basically when we have more intensity, it's like a valley. So it's like, and when we have less intensity, it's like a hill. So the atoms always want to roll to the place where there's high intensity of the light. So we can, and that's for the boxes. Remember, for the boxes, we basically just shine light, and that will trap the atoms there, and then they can flow through the wire.
Okay. Thank you very much.
Yeah.
My name is Nathaniel, and I'm from Kalmar, and I have a question for Professor Alexia. Maybe I missed if you already answered this, but do you or do you not need a nuclear power plant to support a quantum computer? Because that's like a important question.
That's a very important question, and I would say it's under progress. So no, you didn't miss anything. It's currently what some of us are working on right now, trying to have a proper estimation of the amount of energy that we need to run these quantum algorithms, knowing that it's now completely, it's not discussed anymore that we will need lots of resources in terms of gates to do error correction and fault tolerant quantum computation. And the fact that these gates need energy obviously puts the question on the table, but in the end, taking into account the fact that we need billions of gates, how much of energy we need? Which is a different question than, okay, we need a cryostat, and these are the energetic costs that are related to cooling. This we will have to take into consideration, but the energy of the gates is something that we need to consider as well.
Okay, thank you.
Thanks.
Okay, so then I would like to thank all the speakers of this morning that I had the pleasure to chair, and I thank Alexia and Emmanuel very, very much for great talks and for a very nice discussion. And I'm sure you students that didn't pose your questions, you can ask any one of us up here and test if we can explain anything to you, right? Okay, so it will be a pleasure. So thank you very much.
All right, now we continue to the next pair of speakers. The discussion will be after lunch. And the first speaker here is Päivi Törmäe. She is professor in the Department of Applied Physics in the School of Science in Aalto University since 2008. Her research interests range from theoretical quantum many-body physics to experiments in nanophotonics. Long-term interest in superconductivity and superfluidity of fermionic gases. She has discovered a new connection between quantum geometry and superconductivity that may turn out to explain superconductivity in graphene structures and be helpful in the search for new superconductors that even could work at high temperatures, even room temperature. Her group recently succeeded in realizing the first plasmonic Bose-Einstein condensate. I noticed in a paper of yours just 4 years ago, which got almost 600 citations, which is very much for a scientist, and so recent paper. So I was curious, so I looked into it, and then I found that the paper was on a coupling of surface plasmon polariton modes to excitonic states of J aggregates. And J aggregates was something I studied 100 years ago, which is a very challenging, very spectroscopically interesting field, but chemically quite difficult to produce these crystals. So the title of the talk is New Perspectives of Quantum Geometry, Superconductivity and Bose-Einstein Condensation. So we look forward to that.
Thank you very much. Thank you for this invitation. It's really great to speak to such a diverse audience. I know that there are high school students and also scientists here. And even among the high school students, I know that many of you know much more than they teach at school because you can learn from the internet. So I was a bit puzzled, how do I talk now? But I thought that I will talk about some very, very basics, and from time to time I will really go to a kind of conference type of talking for brief periods of time. But the minimum should be that all of you understand what my title means when I finish my lecture. So let's start first from the word quantum, which probably many of you know a lot. So in quantum mechanics, things can have only discrete energies. So for instance, an electron that is bound to nucleus by Coulomb forces, it can have only discrete energies. And you can think Coulomb force as forming some kind of box in space, and then you have different energies. They are discrete. And why is it so? Well, because in quantum mechanics, particles are kind of waves, and you know that you cannot fit certain wavelengths in a box. There is also another thing that comes from this wave-like feature, that these states, you can put them in a superposition. And then waves, you know, they have a phase, like here it's down and here it's up, and it could oscillate up and down. And if you have two waves that oscillate out of phase, they kill each other, that's destructive interference. And then if they oscillate the same phase, they are amplified. And quantum states, you can now put them in superposition of two energy states or some other states, and then these interference phenomena take place. Okay, so now let's imagine that we have many of these little wells, and this would happen in a solid where you have atoms organized in neat rows, and the electrons, they are kind of close to their own atom, but they can also do a quantum mechanical thing called tunneling. They can tunnel to the next atom. This is the picture here. And then, instead of discrete energy state, you form so-called energy bands. So now these things are the allowed energies in the system. They have a little bit of width in energy. And all our technology that we really love, like our computers, iPhones, internet, so on, is based on understanding this. It's really amazing how much quantum physics has done for us. But there is a lot to do also in the future. So that was about quantum. Then, what is Bose-Einstein condensation? Well, there are two types of elementary particles. Fermions, for instance, electrons and many atoms, and quarks are fermions, and bosons, photons and many atoms are bosons, and then there are Higgs bosons and so on. And they behave completely differently when they are together. They don't need to even interact. They somehow know about each other, even if they don't interact, in such a way that fermions cannot go to the same energy state, while bosons can. And now what happens is that if your system has very low energy, very low temperature, the bosons tend to go to the ground state, the lowest energy state, in a massive way. I will soon tell you why this is different from classical systems. Anyway, this leads to Bose-Einstein condensation, which was kind of part of the helium superfluidity phenomenon, but was in a clean form observed only in ultra-cold quantum gases, which were the kind of systems that Immanuel Bloch was talking about. Okay, then about superconductivity, you already know two words, third word coming. So, since bosons can condense, you can ask, can we condense these fermions? Well, obviously they cannot go to the same state, but if you make pairs out of two fermions, they actually form a boson, and then you can condense them. So that's what is behind superconductivity, this phenomenon where electrical current flows without any resistance. So actually in a material, two electrons somehow interact, for instance, via the lattice of atoms or other ways, and they make a pair, and those pairs go all to the same state. And that's an extremely useful phenomenon. So superconductivity can be used to make huge magnets, which you can use here and there. People have been dreaming about transporting electricity with superconductivity because you don't have any energy loss. But that's not very realistic, even when there are some probe stations made. Now, what I think is much, much more important use of superconductivity now and in the future is computing. And you will hear a lot about it tomorrow. For instance, this Sycamore processor, which achieve the quantum supremacy is based on superconducting basic elements and D-wave as well. But it's not only quantum computing where superconductivity could be useful, because you can do also classical logic with superconducting basic elements. This is not so widely known, but for instance, US and China and Japan are building prototype classical computers based on Josephson junctions. They are doing it because you can actually save 100,000 times in energy consumption, in principle. But they, of course, need to cool those devices, because all superconductors now work in really low temperatures. And that costs 1,000 times more energy. So there is kind of a 100 factor there. But if we would have room temperature superconductors, then the whole 100,000-fold energy saving would be there. And this is really important for the world, because your iPhones and computers are probably not the first thing that you will give up to save the planet. So there are huge things that we could achieve. And why don't we still have room temperature superconductors? Because the highest TC is about 150 Kelvin. It's only a factor of 2 to room temperature, and usually a factor of 2 for a physicist is peanuts. I mean, we tend to go orders of magnitude if we want. So what's the problem? And this is something that I challenge all of you to work on. Choose to study physics and solve this, and you can save the world. But now a little bit of hints why it is so difficult. So the electrons interact in these superconductors very weakly, typically. Weakly compared to the kinetic energies that they have. Those are big. And this leads to the fact that the critical temperature, where you can have superconductivity, is sort of exponentially suppressed. This is the interaction. So for very small interaction, this is a big number, and this is a small number. So can we kill those kinetic energies? So then the interaction would be effectively very big. And people have actually thought about that. And you could do it by so-called flat bands. So I told you how these energy bands form. And if you want to use proper quantum mechanics to describe, there is wave function is called a Bloch function. And here I have to tell, because some of you are in high school, you don't know, this is not Immanuel Bloch. This Bloch is Felix Bloch, and Immanuel still has to work hard to become as famous. While I am already the most famous terma in physics, and the most famous baby as well. So usually the energy bands have a dispersion, meaning that if you have certain momentum, you have a different energy. But you can get so-called flat bands where all momenta have the same energy. And they can be approximately flat, meaning that the interactions are much bigger than this bandwidth. And these bands have the funny property that nothing moves. Group velocities are 0. That sounds boring, but it's not, because you can work out by theory what is the critical temperature for superconductivity here, and it has totally different functional dependence than the usual case. And here now you could have pairing, these Cooper pairs at very high temperature. And you can actually make such flat bands. Trivial ones are just, you just confine the particles so that they don't move, but this is not interesting. But you can create them also with interference. For instance, if you have this kind of lattice structure, now you can have a wave function that has minus phase here, plus here, minus here, plus here. And then you can think, if the particle tries to tunnel from here to here and here to here, these pluses and minuses cancel. So by interference, the particles cannot move, and you get a flat band. These are very interesting. Now, I heard all this, that high T, C, and so on, and I asked myself, okay, but why would the Cooper pairs move? Because single electrons don't move in a flat band. And nobody gave me a good answer. So then I thought that this is a good research topic. You should always keep this in mind, that if you don't really understand something, well, sometimes it's just you have to think harder, but sometimes it's that the others don't understand either. They're just talking. And you can really find something out there looking deeper into it. So in order to have this current that flows without resistance, you have to have so-called finite superfluid weight. So current is superfluid weight times the Cooper pair momentum. And according to usual BCS theory, it's proportional to the inverse effective mass of the particles. And that's proportional to bandwidth, and it's 0 in a flat band. So actually, according to conventional theory, there should not be any superfluid, supercurrent. Well, we did the calculation more properly. Basically, we took into account all the bands in the system, not just the band where the electrons live. And we found out that there is a new contribution to the superfluid weight that nobody has ever thought about it. So we found, of course, the usual result also, but we found another term which we call geometric term, and that's directly proportional to the interaction, and then a concept called quantum metric. Now you finally will understand this. What is this quantum geometry doing? And to explain that, I refer to what Finnair is telling people in Europe, that they advertise, take the short northern route to Asia. So it sounds a bit strange that, okay, first you have to fly up to Helsinki and then to Beijing. But that actually makes sense, because the globe is a sphere. So it has a non-trivial metric. You don't take the shortest route if you take the more direct route. The planes actually fly a little bit like this. So metric is nothing but this, that in some kind of special geometries, the distance between two things is non-trivial. And here we go. I explain you the quantum metric, and this is the Bloch sphere, again, by Felix Bloch, and which you already saw in Alex's talk. So if you have two quantum states, you can describe them in this sphere, and any superposition can be described by two angles. And the quantum metric for angle phi is sine theta, meaning that if you are just at this 0, and if you change this phi a little bit and you want to know the distance between the two states, it's actually 0. Because changing, when you have only 0, this is not there. Changing this phase doesn't mean anything in quantum mechanics. While when you are at the equator, this phi changes the relative phase between 1 and 0. And then it has a big effect. So there, the metric is big. So we found that this kind of very abstract thing is connected to whether supercurrent flows in a flat band. Physics is quite fascinating, in my opinion, that very abstract things lead to very practical consequences. And we derived a lower bound for whenever we have so-called Cher number non-zero in the band, we will have superconductivity. And I don't go into this, I just tell that this Cher number is a topological quantity in the same way as when you have a Möbius strip, you can have one winding and you cannot move it. Okay, so where would we then find the material where we have a flat band and can really build it? There are many candidates, but one promising one is 2 graphene layers, where there was a really beautiful experiment 2 years ago. Here are the energy bands of the 2 layers. You tilt them by some angle, and at some magic angle theta, you will see a flat band forming. And exactly there, they observed superconductivity. Well, it's not yet in room temperature, it's in 2 Kelvin, but I think this type of materials, which you engineer, for instance, by stacking 2D layers, are the promising route to find these flat band superconductors. And our group and a couple of others have already identified that this flat band, this geometric concept and geometric contribution is important there. Okay, so that was about superconductivity, and now I go to the Bose-Einstein condensate, and I like to note that the previous results that I showed were our theory work, but we are also doing experiments, and here I show our experimental results. But first about the Bose-Einstein condensate, you might also think that simply in a classical system, if you cool down things, they like to go to the lowest energy state. So what's the special thing in Bose-Einstein condensation? What's the quantum thing? Well, the thing is that in the quantum world, they go to the ground state much, much more than they would go in a classical system. And this comes just from statistics. Think that you have 2 balls or particles, 1 and 2, and you can put them in 2 boxes, blue and red. In the classical case, or if the particles are distinguishable, yeah, you can put them like this, both in the same or in different box. But if they are indistinguishable quantum particles, then you have only 3 choices: in the red box, in the blue box, or that the particles are in superposition of one being in the blue, one in red, and one in blue. 2 in blue and 1 in red. You must write it like this. And this then, if you work out the statistics, leads to the fact that if you calculate the number of particles in some state, it follows this Bose-Einstein distribution, and you see if this thing becomes 1, this explodes, so you have huge amount of particles in one state, and it's the ground state. And you can manipulate by changing the temperature. So this has been observed in many systems already, but we wanted to stretch this concept. First of all, to observe it in room temperature, where there are only few examples of previous room temperature condensates. And second, we wanted to go to time scales where nobody has been, to ask how fast can such a thing form. Because to form the condensate, you have to have so-called thermalization, where the particles somehow find the ground state, either by interacting with each other or by interacting with some other particles. And this we achieved 1 year ago. So here finally comes the light in the nanoscale. The objects that we want to condense are excitation in so-called plasmonic lattice. So these are metal nanoparticles that we fabricate on glass. And nanoparticles can act like little antenna or dipoles. They take radiation, emit radiation, and they confine also light around them in some kind of near field. And this is special because the scale of the particle can be like 10 nanometers, but still it has light around it. And light wavelength in free space is 0.5 micron. But by taking also the electrons into the game, you can really confine light to nanoscale. And it can have extremely high fields then. So then when we arrange the particles in a periodic structure, we will get these band structures, as I already showed, with little band caps. And we want to condense the particles here. And the particles are like a combination of light, mostly light, but also electron motion in the particles. And the challenge there was that they typically live in the lattice only 100 femtosecond. So it's extremely fast scale to manipulate and monitor things. But we found out how we can see what happens in this extremely fast timescale. We did the experiment in this way. So we have here cold nanoparticle array, then some liquid with diol molecules, IR792, and then we pump the molecules with femtosecond lasers so that they go to the excited state, and then they can emit light and so on. They can emit light to this lattice, and the light propagates here. It also scatters all the time a little bit up. And then we follow what happens along the propagation. And now that somehow turns distance into time. We can see what happens in the beginning, in the middle, in the end. And to understand what we are doing, there are now two important concepts. One is the band edge energy. We can change this easily by changing the distance between the particles. And then our molecule has absorption and emission spectrum. And this energy where absorption is very, very small, effectively is important. I call it absorption edge. And this is how the thermalization works. And thermalization is the process where we put the molecules and the light particles in high energy first, and then they go to low energy. And in this case, the light interacts with the molecules and loses energy in that way. So this is the thermalization. So we start by having this absorption end a little bit lower than the band edge energy. And we pump the molecules, they emit to our lattice. Then the molecules also absorb the light back. Then, because the molecules have vibrational states, you can kind of push the energy in the vibrations and lose some energy. So you emit photons that have low energy. But now even at the band edge, you can still absorb and go to the lower branch of my dispersion. And this is what we see in the experiment. So here is the position in the lattice. This is the energy that we observe. Energy of the light that we observe. And first we see high energy light, but along the propagation you can see this kind of redshift, decrease of energy of the light. And here is the band edge, and it jumps there. And we can integrate the light on this band edge. We see that there is never very much. So this is how the thermalization works. And now if we want to condense, we have to match these two energies. And now you still have the same process: emission, absorption, loss of energy, emission to the band edge. But now there is nearly no absorption left. So you will get this phenomenon of Bose-Einstein condensation, where basically light particles enhance other light particles to go to the same state. And this looks in the experiment like this. We have this redshift of the light, and then at some point in the array, after some propagation, we see this bright feature, which is the condensate. And in this type of condensate, because what we observe basically is light, it's very important to distinguish between usual lasing phenomena and this condensation. And here we can do it very nicely. We put the band edge in a very low energy, and here we now, in terms of lasing language, we have very high gain for the band edge immediately, and we see only lasing, so we see very bright feature at the band edge from the beginning. So now I will snapshot our most recent results on the BC, and I will go to quite technical things. But So we wanted to really understand that how can this thermalization happen so fast, because we know from our experiments everything happens in below 1 picosecond. In this experiment, we went to so-called strong coupling regime of light and matter. Professor Ebbesen will talk about it more. And we pumped over the whole sample. And now what we see is quite different behavior. So this is the pump fluence, this is the output intensity. We see a double threshold. First threshold corresponds to lasing. Here at the second threshold we see the BC, and now we have much better signal to noise than in the previous paper, of course. So we see very nicely this Bose-Einstein distribution tail over very long range in energy. So that's fine. These are phenomena that we understand. Then there was this middle regime of pumping where we see this kind of picture. So these are just photographs of the sample, real space images. These are spectra spatially resolved. So we see some kind of curious phenomenon. There seems to be this redshift, this thermalization going on. And the interferences correspond to the K vector of this energy. But what is really going on, we made samples of 3 different, or actually more, of different sizes, small, medium, large, and otherwise the same conditions, and the pictures look completely different. So this was puzzling. But then we realized that in all, this kind of more empty area, or low intensity area, has the same length. And then we realized, and what is going on is a stimulated pulse formation. So if you have a rate equation simulation of that kind of process, it goes like this. You have a pump pulse, then population inversion builds, and then you get the output pulse. And this distance here is so-called pulse build-up time. And that's this empty area. And now, if we think that we have these pulses forming at each point in the lattice and propagating while they form and die, then we will have less intensity here because nothing starts outside the sample. And this length of this area only depends on the pump pulse intensity, so we can vary that, have different sizes of arrays, and measure this empty distance of one. They are all in one line. So we have shown that the thermalization in this system is actually a stimulated process, and that's why it can happen so fast. We extracted that it happens in 100 to 200 femtoseconds. And for instance, if we have a 500 femtosecond pulse, pump pulse, which is kind of too long for the formation, we don't see the BC at all. Great. So this is a summary, but I will not stop. So there will be a movie in the end. But the main point was that you understand the title now, that quantum geometry can actually give these flat band superconductors, which may be the route to realize superconductivity at room temperature, which would be really important for the power consumption of our IT. And then we have a Bose-Einstein condensation in a time scale that nobody has done before, and we have shown that it can happen because of the stimulated processes and strong coupling. And here are my wonderful collaborators who have worked on this project, and now the president of Chalmers was advertising that you can come to Chalmers. You can also come to Aalto. It's not that far away. Maybe from where you are, actually, it can be closer than Gothenburg. And finally, I will show this Bose-Einstein condensate presented in the form of a video.
In the quantum world, particles possess both particle and wave-like characteristics. When the particles are cooled, they act increasingly like waves. They also slow down and their energy decreases. Bosons are particles which are allowed to have the same energy at the same time. For instance, photons, the light particles, and some atoms are bosons. At a sufficiently low temperature, the waves of the bosons overlap, and all of them can be described by a single collective quantum wave. This exotic form of matter is called a Bose-Einstein condensate. It was predicted by Albert Einstein and Satyendra Nath Bose nearly 100 years ago, and it took until 1995 to achieve the first experimental Bose-Einstein condensate made of alkali atoms. At Aalto University, Finland, researchers have created a condensate of so-called surface plasmon polaritons. These particles are mixtures of light and electron movement in metal nanorods. Unlike most previous Bose-Einstein condensates, this new condensate is formed at room temperature. Let's take a closer look at the surface plasmon polaritons. Tiny rods of metal can be made to resonate along with incoming light. This so-called surface plasmon resonance can be tailored by assembling the nanorods into a periodic array. Light gets trapped between the nanorods, and the light is coupled with the electrons in the metal. This produces a hybrid particle of light and electrons in motion. As an energy source, the researchers use dye molecules placed on top of a gold nanorod array. By exciting the molecules at one end of the array, it is possible to monitor the propagation of the particles that form the condensate. While propagating along the array, the particles meet only molecules that can absorb light. Then the molecules emit light back to the array. Because the molecules vibrate, some energy is lost over each cycle of absorption and emission. This so-called thermalization is seen as a collective shift of the particle population towards smaller energies, that is, from shorter wavelengths to longer wavelengths. When the lowest possible energy in the array is reached, the particles form a Bose-Einstein condensate. This is seen in the energy spectrum as a large number of particles in the lowest energy state, together with thermalized particles at higher energies, as described by the original theory by Bose and Einstein. The condensate shows coherence over distances that are large compared to the case of individual particles. This is analogous to the overlapping waves in atom condensates. The condensate forms in a picosecond, which is 1/trillionth of a second. How is it possible to observe something happening so fast? The key is in the experimental setup. By exciting the molecules only at one end of the array, it is possible to observe the light emitted by the forming condensate at each position in the array. Knowing the speed of the particles, the surface plasmon polaritons, the position in the array maps directly into time. This opens a window to the underlying ultrafast dynamics.
Thank you.
Thank you, Päivi. Very exciting talk. And there will be possibilities to ask questions at the joint question discussion after the next talk by Stefan Hell. So now it's time for lunch, and we resume here at 1:15, right? Welcome back. Are you hungry for more science now? Very good. So the next speaker is Stefan Hell, born 1962 in Arad in Romania. And he's the director of two Max Planck institutes, that in biophysical chemistry in Göttingen and that for medical research in Heidelberg. Stefan was first to break the record of overcoming Abbe's diffraction limited resolution barrier in a light-focusing fluorescence microscope. For this accomplishment, he received numerous awards, including the Nobel Prize in Chemistry in 2014. Stefan received his doctorate in 1990 in physics from the University of Heidelberg, and from 1991 to 1993 he worked at the European Molecular Biology Laboratory, followed by stays as senior researcher at the University of Turku in Finland. I think that was very important. 1993 to 1996 was that, and he also worked as visiting scientist at the University of Oxford. Hell holds many honorary professorships and doctorates. And his speak today is mini-flux, nanoscopy, super resolution, post-Nobel. We could interpret that in different ways, but we look forward to hearing.
Thank you very much, Bengt. Thanks. It's a great pleasure to be here. Thank you for inviting me. I'm going to talk about the resolution and making, say, progress in this field after the Nobel Prize. This is how it was meant. Now, in the 20th century, as you know, the resolution of any light-focusing microscope, a microscope that uses just focused visible light, was limited to about 200 nanometers. Now, the turn of the century showed that, at least for fluorescence microscopy, there is physics or physical chemistry that allows you to overcome the diffraction resolution barrier, and you can achieve a spatial resolution that was totally unanticipated. As a matter of fact, stat microscopy, which was the first method that proved that, allowed us to achieve a spatial resolution that is larger by a factor of 10, for example, down to about 20 nanometers. Now, as Bengt just mentioned, this has led to the 2014 Nobel Prize in Chemistry, and this is the official poster of the Nobel Foundation, showing, of course, the basic principles of stat microscopy and showing the basic principles of palm or storm microscopy, which was demonstrated a couple of years later and had a number of advantages over stat. Of course, also disadvantages, many things in common, many things different, but one thing that it clearly had in common with stat, that in principle, you could attain a spatial resolution that was at the size of a molecule. Now, if you really look at it, I'm saying deliberately, in principle. In practice, the resolution was not better than, say, resolution improvement was not better than by a factor of 10. So in practice, you couldn't get more than about 20 nanometers. Of course, there were exceptions. So with that, with a number of cases, so special fluorophores in solid state, you could get down to the single-digit nanometer range, and also with palm storm in a number of special cases, but not in general. So in my view, the Nobel Foundation put it just right. Their microscopes, meaning the laureates' microscopes, crossed the threshold. And what I'm adding to this, but did not attain the ultimate limit. And so the actual title of my talk and the actual motivation for the work that I'm showing now is to do just that, attain molecular size resolution with focused visible light, of course, in 3 dimensions. Now, in order to explain to you how we get there, actually we got there, as you would see, I have to make you acquainted with the basic principles of operation of this breaking of the diffraction barrier in fluorescence microscopy. Now, especially if you're, say, high school student, you may think, okay, so why don't we get there? But you may have already learned it in school that the reason why it's not possible, say, usually to get to a higher spatial resolution than about 200 nanometers is actually very simple. It's the fact that a lens cannot focus the light down to the size of a point of a single molecule, for example. If lens could do that, of course. We could just direct light just on a single molecule. We could single that molecule out, so to speak, and then address each of the molecules here. And of course, we would have molecular resolution. We could collect the fluorescence, for example, in fluorescence microscopy back here at a detector. And just by scanning with this point-like focus, we could just address each molecule and have a molecular scale resolution. But that doesn't work because light propagates as a wave. And because of that, the lens is not capable of producing a single spot of light that is a nanometer size or so, or even smaller. Rather, we'll get a diffraction-limited blob that is at least about half the wavelengths in dimension. And because of this diffraction phenomenon, it's not possible to address a single molecule. Rather, what will happen is we will address all the molecules that fall within this spot size range, and then all of these molecules will kind of be flooded with light. They will light up and produce, of course, backscattered light. Now, in our case, the backscattered light is fluorescence light, so light of a slightly longer wavelengths, which is collected here in the detector. And now you can imagine that each of the molecules, of course, also produces a wave of fluorescent light that is also diffracted. And even here at the detector, of course, we will get this diffraction blob for sure. And then each of the molecules here will produce a blob of light that will inevitably overlap in space due to the finite size of the spot, of course, of fluorescent light in the detection range. And as a result, it's not possible to tell the molecules here apart at the detector. Now, the solution to this long-standing problem in the end was very simple. Guess what it was? Just make sure that not all the molecules that are covered here by the light are in the end capable of scattering light back. In the case of fluorescence, you have to put them in a state, in a molecular state, in which they are not capable of producing the light back. So in simple words, you can say you have to find a way to turn some of the molecules off. For example, turn all these molecules off but this one, and then you can separate this molecule from the rest. And then, of course, you can behave, the system can behave as though it would have addressed just this molecule. And then you can sort out this mess in here, and you get a signal just from that molecule. So actually, if you will, the basic element that really created the field and still is the foundation of the field is to implement an on-off transition here in the focal region so that not all the molecules that inevitably flooded with the green light are capable of producing signal at the end. Now, in STED microscopy, without going into details, this phenomenon that turns the molecules off is called simulated emission. It just kicks the molecule down to a ground state in the case it gets up, so it keeps the molecule constantly in the ground state, keeps it off, so to speak. But this is just one way of doing it. There's many other ways in many other molecular transitions that allow you to turn molecules off. So this was just the starting point. And there are also other mechanisms, for example, like cis-trans isomerization or electron transfer and so on, to do the same thing. But in the end, it's on-off. Now, STED microscopy has the hallmark that we use a beam of light that turns molecules off. And this is why I'm showing you this red little thing here. It is a beam that has a hole. And wherever there is light, the molecules are turned off. And if there is no light, and this is the case at the very bottom of the hole, it's a donut-shaped beam, the molecule is not turned off, and then, of course, you single out that molecule, for example, and so you can separate this molecule from the rest due to this on-off transition. Okay, now Palm Storm. What's the difference here in Palm Storm compared to STED? Again, you play on-off, so that's the same thing, but the way the on-off is played is substantially different. Here, a molecular transition is chosen, such as a cis-trans isomerization or so, that turns just one molecule on within this subdiffraction range, and the rest is off, and this is how we can distinguish this molecule from the rest, but purely stochastically. You could do it by a beam of light, where every now and then there comes a photon that turns molecules on. You can do it thermally. There is a way of association and dissociation. There's many ways of turning molecules on and off, as I said. But now, of course, if it's purely stochastical, there's no way to know which of the molecules have been turned on. So it could be any of these molecules that I've shown here. And of course, you don't know where this molecule is located. And therefore, you have to find it out. And this is possible if you place a detector in here that has many, say, detection points, an array of detectors that gives you a coordinate. And that's the first condition. And the second condition is that many photons are emitted from the molecules consecutively so that you can associate these photons to that particular molecule in the on state. And now, if you're getting, say, n photons, 10, 100, or 1,000 photons from that molecule, you will get a pattern of light in here. And then you know, of course, that the center of that pattern must be associated with the position of the molecule, because there, where the pattern is brightest, of course, this must be geometrically just related to the position of the molecule. And so what you do is you find out the position of this on-state molecule that you are detecting just by calculating the centroid of this diffraction pattern with a photon number n. So n is like 10 or 100 or 1,000 or even more photons. And the more photons you have, of course, the better you will know the position of the molecule. Okay, so this is the concept of Palm, and if you compare it now with the concept of STAT, to see the similarities and the differences, as I said, on and off, this is the basis of both. But the difference, of course, is in the way you find out the coordinate. Here, of course, you need many photons to find the position of the molecules, and here, of course, you need many photons to define the position of the molecules. Because the brighter this donut beam is, the better defined will be the zero in here, and the better defined will be, of course, the position at which you know that the molecule will be located. And it's very obvious. If you have just one photon within the diffraction zone, just one photon, imagine a beam of a single photon. It could be anywhere, go anywhere within the diffraction zone. There's no way to create a pattern or define a position. But if you have many, the more you will have, of course, the better you can define the zero in here or the position in here. So the secret to having or to getting a position optically with photons is to have many photons. But the way it's done, as I said, is different. Here the many photons come from the laser. They define the position here. And here the many photons come from the dye. And this is a big difference. Why? If you have to do the coordinate with the many photons that come from the dye, you have to rely on the fact that the dye is bright and emits many photons. So this backscattering of fluorescence is very, very strong. But fluorescence, I can tell you, is not something reliable. It is very unreliable. The dye bleaches, the molecule goes to a dark state. So doing it in this way, say with many fluorescence emission, is not very reliable. And this was the reason why Palm Storm never got beyond the 20 nanometers, because at some point the fluorophore didn't emit enough light, and it takes, of course, a lot of time to collect all these photons, and by the time the molecule has moved, and this is a problem. But here, you have zillions of photons. They come from the laser. No problem in putting in as many photons as you want. The laser basically gives you an infinite number, almost infinite number of photons, because there's no shortage of photons from a laser. And you can perfectly define the position here of the zero. So if this is the case, why not combining the strengths of the two methods, so to speak, and come up with a method that is a synergy of the two? And what is the strengths now? Well, it's very obvious. Palm already deals on the separation level when it comes to separating features on the single molecule level. And there's no better separation than separating single molecules. There's an advantage. As I said, the disadvantage is the way the position is found out. Here, of course, the strength is to find out the position. So why not combining the two, say, doing the separation on a single molecule level, like in the Palm concept or Storm concept, but doing the positioning in the way it's done instead, with the zillions of photons that come from the laser. And if you combine the two, you must get a higher spatial resolution and better pictures. So that has been the logic behind this. Now, in the case you didn't really listen to my talk for some reason, I don't know, maybe you were interested in the way I look or whatever, or my baldness or so on, you can start now from scratch, okay? I'm explaining everything from scratch, and I'll make it in the easy way. Let's assume now we have turned on the molecule, and this is the molecule. Play on off, we have turned on just one molecule. Now, what people usually did, also for the Palm Storm Nobel Prize winning concept, they had so flat illumination of light in the focal plane of the microscope. You see it here. This is the objective lens, a flat illumination of light. And then this molecule produced fluorescence. It was focused on a camera. This is the camera, the pixelated detector, so to speak. And then, of course, the fluorescent light that is shown here on the monitor of the computer is diffracted because of diffraction. So here, the lens, of course, produces a diffraction blob of light here on the camera. And then, as I said, people understand by localization, calculating the centroid of that pattern. And as I said, the more photons you have, fluorescent photons you have, the better you will know the position of the molecule just by calculating the centroid. It scales with the inverse of the square root of the number of photons. So if you want to have a 10-fold higher spatial resolution, you need 100-fold more photons. Okay, but this is not how we're going to do it. Because we're doing it now, the localization, in the STAD-like way. So we're going to use a pattern of light. We are going to use, so to speak, a donut. The donut is very good because the donut itself, or the donut zero to be precise, perfectly defines a coordinate in the focal plane. So you see, this is the maximum of the donut. Here there is a 0. So here in the intensity 0, there is no light, and this is perfectly defined because we have so many photons from the laser that perfectly define, say with sub-angstrom precision, if you will, the position of that 0. Not only that, we can measure if the fluorophore is right at the center of the donut, because if the fluorophore, if the molecule is right at the center of the donut, it cannot emit light because there is no light. It's a zero intensity. So if the molecule is slightly off, it will emit light, and then we will know, oh, it's not at a 0 because there's some light coming. And this helps us, of course, easily to find out where the molecule is actually located. Now, since my last name is Hell, and we spoke about demons this morning, I said, okay, I have to introduce a little demon. So this is my little demon. And this little demon has a piece of information that humans don't have. And in this particular case, this little demon knows where the molecule is. And let's assume now for the moment, we do a Gedanken experiment, a thought experiment, as it is done with demons, that this little molecule moves, and the demon, knowing where the molecule is, shifts actually the excitation beam in such a way that the 0 of the donut always coincides with the molecule. Okay? So what does that mean? If the 0 of the excitation beam donut always coincides with the position of the molecule, of course there will be no fluorescence emission. That's very clear. Not only that, the demon can perfectly trace, of course, the position of the molecule simply because the actual, say, actuation on the beam deflector, or the position of the donut, would be identical with the position of the molecule. So the demon can perfectly trace actually the position of the molecule. So what can we infer from this? In this Gedanken experiment, of course, the demon can perfectly localize the fluorescent molecule without requiring any single fluorescence emission. Without any detection of photons or anything, there's no fluorescence emissions going on because the 0 of the donut perfectly coincides with the position of the molecule. And this is contrary to the normal localization where you need many photons. As I said, n photons, 10, 1,000, 100 times is even better to get a factor of 10. As I said, the more photons you have, the better localization, but here you don't need any fluorescence emission in this thought experiment. And then there comes a shocking other conclusion that might surprise you, especially if you're trained as a physicist. Will there be a wavelength dependence here? Not really, because if the molecule is slightly off the 0, who cares what the wavelengths of this donut is? So there is no wavelength dependence, say, in this limiting conceptual range. And so this means that the idea, so to speak, of localizing the molecule with a pattern of light, in this particular case with a donut, is very profound. I'm going to show you this now. Now, in reality, there's no demon, of course, and also, even if I'm named Hell, I have to work with something that works. So we have a controller, we have a detector, and of course, we have this beam deflector that can shift the donut around. And then what we do is actually we measure the fluorescence that is produced if the donut is slightly away from the position of the molecule. So if the molecule starts moving, of course, we of course try with the controller to shift the donut excitation beam just on the position of the molecule so that the 0, of course, coincides with the position of the molecule, but we will fail because we're not demons. But what we will see, we will get a detection of light, so fluorescent light, that is measured here. And that, of course, is fed into the controller. And this fluorescent light gives us actually a clue where the molecule actually is. And we can use, of course, this information to reposition, of course, the donut. But we have to do this only by a little, of course, because, say, if it's slightly away from it, you don't need many photons, so to speak, to find out the position of the molecule. And this, of course, helps you to find out the position of a molecule here with a minimum amount of fluorescent photons. Why? Because the fluorescent photons that are detected in here are just used for refinement. You don't need to have 100, 1,000 or so photons in order to get a position with a certain precision. Okay, now you will ask, okay, how do we do that in practice? How do we know where the molecule is located, or what does the controller actually do, in other words? It's very simple. Now let's assume the molecule is in here, okay? And we don't know where the molecule actually is, so we put it in here in this view graph. We assume the molecule is somewhere within this range, within this line. I'm just assuming one direction because it's easy to explain the concept in a single direction only. And now, it's very obvious what we would have to do. We would have to scan this donut across the molecule to find out the position where there is no fluorescence emission, because then we know where the molecule is, because there, the zero of the donut, whose position we know, of course, must coincide with the position of the molecule. So this is the intensity profile of the donut, and this is the fluorescence that we get. Now, let's move, and you see, now, the zero is there, and the fluorescence is minimum. And in this way, just by scanning, of course, with the donut across the molecule, we find the position of the molecule, we know where it is. Now you say, oh, this is a quite tedious thing, because you have to scan all the time to find that little position. No, you don't have to do that. Because if you know that this is, for example, a quadratic function, and usually the zero in first approximation is always a quadratic function, it's perfectly enough to know the endpoint, say, of the signal from the endpoint, so the counts of flow force that you have at the endpoint of the two traces of the trace, and 0 and 1. And then, of course, you can extrapolate, because you know this is a quadratic function, on the actual position xm. It's very simple. It's basically algebra, 7th graders algebra. You can easily calculate that. So if you assume that you have a quadratic approximation here of the intensity at a donut, you can just, say, invert a simple quadratic equation, and you will find out that the position of the molecule is given by this distance L, in which you assume that the molecule is located. Usually that's a diffraction range, say 200 nanometers or so. And you just take the ratio of the two endpoints, of course, of the fluorescence of the two endpoints, and then instantly the position pops out. So if the two are equal, of course, xm is in the middle. Now, this simple equation is actually surprisingly profound, because one thing it's telling you that there's no wavelength dependence. Gone. There's no wavelengths in here. So, no. You just find it out by ratioing the brightness of the two endpoints, of the measurement at the two endpoints. And not only that, there's no dependence on the molecular rotation. You will know that usually, I mean, this fluorescence emission is it's a dipole emission, and then the orientation of the molecule matters, of course. And this is a big problem for this palm store concept, because due to this, the resolution can be degraded by 10, 20 nanometers, even more, because the centroid of that diffraction pattern is off by 20 or 30 nanometers. No one has sorted out this problem yet, so it's all kind of sometimes pulled under the carpet, but here it's inherently gone. Because the only thing we do is we inject position information with the donut. The donut injects position information, and then finally we take this ratio, and that's it. Now, of course, there is an uncertainty still left with xm. It's not perfectly defined, and that will depend, of course, on L and the range of uncertainty that we have to begin with, and of course on the brightness of the molecule. So the higher the number, and 0 and 1 is, of course, the more precise the sigma will be, so the smaller sigma will be, and the higher the precision, hence also the spatial resolution that we get. But the good thing now is, and that's the fundamental difference to the concept before, here it scales linearly with L. The square root of n is still there because of Poissonian statistics. But here, you have a handle on it because the uncertainty scales with this range L. That means once you have coarsely estimated, oh, it's not within the 200 nanometer range, it must be somewhere here with 50 nanometer uncertainty, you just scale down L. And this is, of course, more effective than waiting for more photons as you do in Palm Storm, because this scales with the square root, which is not so good. It is damned. As I said, for 10-fold higher resolution, you need 100 times more photons. But here, if you decrease L by 10-fold, you get 10-fold increase in spatial resolution. So it's more effective to zoom in on the molecule and then do the same thing again. And so you can iteratively actually, say, so to speak, approach the position of the molecule, thereby reduce the number of fluorescence photons that you need to detect in order to find out the molecule with a certain precision. And this is why this concept is so effective. Okay, now, of course, this was in 1 dimension. How you do it in 2 dimensions or in 3 dimensions. If you do it in 2 dimensions, of course, you need at least 3 points. It's better to use 4 points to avoid ambiguity, so that's what we did in practice. So measure here, with the donut 0 placed here, 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 and here. Take the 4 numbers, and then the equation is not that simple anymore. It's a more complicated function, but in the end, it boils down to the same thing. You see here the uncertainty, which boils down to, or comes down to the resolution in the end. Again, you scale linearly with the range in which you anticipate the number of molecules, and of course, square root of n, that's there, but we can outperform the square root of n behavior just by zooming in, so to speak, on the molecule, by making the L smaller, and then and quickly finding out where the molecule is by overlapping, so to speak, the 0 of the molecule, at the 0 of the donor with the molecule. Okay, how does this compare with a normal, say, camera-based localization? And you see it here. So this is the number of photons that you need, and this is the precision that you get. This is for a realistic camera. This is actually a measurement, and now you see with 10 photons, you get, in our case, we call it min flux because it has this minimum in here and produces a minimum of fluorescence flux for attaining a certain precision. You need only 10 photons. With only 10 photons, you get 10 nanometer spatial resolution. But if you then try to do the same thing with a camera, you would need 29 times more photons, so 290 photons in this particular case. So we are more efficient in terms of the fluorescence photons that we need. And this is actually a theoretical calculation, so-called Kramer-Rauerbaum. Kramer was a Swedish mathematician. You see here, this is the equation for the uncertainty that comes out. Now, again, zooming in on the molecule is the key, because this helps you getting up the precision without requiring more photons. But in the end, of course, you have to prove that you get better images. I'm going to show you this. Again, this is just a conceptual description. In order to separate the molecules, let's assume this was an object, we have to turn the molecules on and off, so this has not changed since that, again, but it's done on a single molecule, say, level, as it is done in Palm or in Storm, and then we localize the molecules and then get a picture. Or you can also do tracking, and you will save the number of fluorescence photons that you require in order to track the molecule with high precision. Now, this is now a cartoon showing, say, fluorescent molecules at very small distances. You see here 11 nanometers or so. At the time the Nobel Prize was given, this is a Palm Storm recording, these molecules could not be separated. Neither with Palm Storm nor with that, because they are too close. The resolution was not there. I said about 20 nanometers was the maximum resolution. Now with this min flux concept, you take them apart. You turn the molecules on individually, locate them with the donut, and here you have it. So basically, we are down to the range that is the range of the size of the molecule, which is of the order 1-2 nanometers. There's a link or so, but it's basically down here. 6 nanometers, so distances. Okay, again, Palm Storm cannot resolve it. Min flux takes it apart. So in other words, take into account the fact that we use just focused visible light. We have reached molecular size resolution, essentially, with focused visible light. I mean, 25 years back, I think it's fair to say, if someone just stood here and say, oh, one day, not very long from now, so to speak, 10 years back, 15 years back, one will be able to attain molecular scale spatial resolution with focused visible light. People said, this guy is totally nuts. This is not going to work. No way, but here it is. Not only that, of course, you can take large field of view data, of course, with high spatial resolution, because you can scan the donut over a large field of view. Why not? And then you zoom in on each molecule that is there, and I'm going to show you now large-scale pictures. And here, these are, again, nuclear pores, similar to what you've seen on the Nobel poster. But now, you see, basically, this is the resolution that we have. Essentially, these are individual molecules here, labeled molecules. Again, very nice, very nicely resolved. And as I said, the spatial resolution is on the range of about 2 nanometers in sigma or so. I compared it with that, which won the Nobel Prize. And I'm comparing it with confocal microscopy, which I shouldn't do. Honestly, I feel sorry about those people who still use confocal microscopy, but, well, that's it for the moment. And you see now the evolution that has happened. it's here, between here and here, it's a factor of 100. So it's quite a difference. And now, again, I'm showing you this was also with fluorescent proteins. Here you have the data, so the median here of localization precision is 2.3 nanometers in sigma. Not only it works for fixed cells, it also works for living cells. That's important. This was done by focusing into a living cell on the nuclear envelope, again with a fluorescent protein. And also it works in 3D. So biologists want to have something that also is obtained inside the cell in 3D. Now this is 3D data. The color encodes height, by the way, but you see, say, the impression of height in Z very, very clearly. Again, the Z resolution is as good as the X and Y. You see here 2.6, 3.1. Is another rendition in 3D. So this is a nuclear envelope, and it's showing again that this is true 3D data. Now you say, if it's spotty, it's because it's molecules. And the challenge now is for the real chemists, of course, to do fantastic labeling that really labels every molecule that you want to see. So the challenge is now basically with the organic chemists to get good labels or to do the labeling perfectly right. But from the physics, from the concept or so, I think this matter is virtually closed, if you ask me. Having reached now this resolution, it's very obvious. But of course, biologists say, can you do 2 colors? Of course we can do 2 colors. This is showing you two different types of fluorescent molecules, and this is a 2-color recording. Of course, we can also do 2 colors in 3D. This is engineering, if you will, if you see it from a scientist perspective. But it's important engineering, because in the end, the biologists want to use it and they want to get pictures in 3D. They want to find out something biologically interesting or medically relevant, but I'm sure they will, because the resolution increase is now so much over the diffraction barrier that I have no doubt that major discoveries will be made in the life sciences as a result of this fundamental change that has happened in the last 20 years. And so this is a 3D rendition, of course, of a certain protein in the synapse, and definitely one of the applications that will come in the next future is that you really sort out the molecular maps of anything you can imagine, the nucleus, the synapse, the immunological synapse, whatever. So there's many other things. There's another important aspect. Because you need fewer fluorescent photons, you can also image much faster. This is also important. And I'm showing you this now. We made a little experiment where we attached a fluorescent molecule rigidly to a surface with a piece of DNA. And this is a localization now down to 2.4 nanometers by measuring 4 points in here. And then, of course, we took another type of molecule that was allowed to move. Okay? Not quite like that. It's just a cartoon. I couldn't make a random movement. In fact, it was a random movement. And then, of course, the localization spreads out over here. You need much fewer photons to get the same, say localization precision. So you get a time resolution for the same precision of localization that is substantially better, order of magnitude better. And this is just the traces for the experts of you to show you that this is clearly vindicated, this movement. And this is now not just a random cartoon. This is the actual movement of that molecule in this focal plane. So it really moves like this. And so the reason why I'm showing this, so one can imagine now experiments at a very high speed. So you label something like a protein, and the protein starts to fold or something. You can get the movement within a short period of time with very high precision, with nanometer precision. No way to do that with a camera, because the camera you have to wait until 1,000, 2,000, 10,000 photons come in order to find out the position. But here, using this donut that defines already a position and use the fluorescent photons only for refinement is so fast. This will open a new area of application. So summarizing this, the resolution is basically down at the molecular size. And if you calculate molecular movements of 10 microseconds, so within a short period, should be possible in the 10 nanometer range with 1 nanometer precision. And if I was a biophysicist and maybe 30 or 25, I would just go for this, because there is plenty of things to discover, because this dynamic range no other method can offer, and in a living cell condition. This is important. Now, as I said, there are new fields of application like molecular maps or looking into molecular dynamics and so on. But the good news, and here, of course, I'm biased. I say, speaking very openly, I have shares of this company. This company has released last week actually a commercial version of these systems. Of course, they do get the same resolution as we do get in the lab, because it was founded actually by my former PhD students, postdocs. And of course, they have a high spatial resolution. This is a lipid actually, in a lipid bilayer. See how quickly you can actually see this movement of the lipid. And in essence, you can buy it and you can use it. I think this will speed up, of course, the application of this new method. Now, for the physicists, a few insights. There is no optical nonlinearity used in here. So when I was a student in the 80s, I knew, of course, that using some nonlinear optics, you can overcome the diffraction barrier. But this was kind of leading the wrong direction. There's no optical nonlinearity used in here. And the second thing, there's no dependence on the wavelengths of the resolution. If you think the way it works, there's no dependence anymore. Because what you do actually, you match actually two singularities. One is the molecule, and the other one is the zero. And in the first approximation, the wavelengths, as I indicated with the thought experiments with this little demon, doesn't really matter. And there's also something very heretic if you think about it. No wavelengths dependence in a focusing light microscope and resolution. I mean, this is crazy. Anyway, it shows science is crazy at times. So with that, I'm acknowledging the people who have really contributed to this development. I don't have a big group anymore. Fortunately, these two guys left already. They went to industry. So these are still in my lab. Actually, Yasmin Pape is a PhD student, and he's Francisco Balzarotti, a clever postdoc who is now becoming a professor in Vienna. They've done great work, of course. And of course, also me, I'm looking for clever people who are motivated to make a fundamental difference in science. Thank you very much.
Those who have had doubts whether Stefan deserves a Nobel Prize, I think the doubt is removed completely now. So you may keep it. So depending on political bias, you may choose either the right hand or the left hand chair there. And maybe you go first, ladies first.
No, you can choose.
And please, everybody
It depends whether it's from the audience or from the back.
Oh, I see.
Questions? In the meantime, I could ask, you asked us chemists to do something about the molecules. Normally, the emission dipole is assumed to be a point dipole, but of course, in reality, it has some extension. Is that something you...
It may play a role at some point, yes. That's definitely the case. I mean, if you localize it, you always get the average. You don't get any substructure. But if you, of course, really play to the very end, that, so to speak, the zero becomes so well defined that you have a strong intensity gradient over the size of the molecule, then the dipole approximation breaks down. Because dipole approximation, of course, assumes that there is a constant field more or less over the molecule. This is something interesting to pursue. It may be useful or may lead to something interesting. But probably not for biological applications, because the biologists, they don't care about the fluorophore. They just use the fluorophore as a proxy for the proteins that they want to see. Actually, so in that sense, it probably won't lead any further in the life science application, but it may lead in the molecular spectroscopy to some new insights, like seeing the shape of the molecules optically.
Okay, first question. Please ask whom you are asking.
Hello, my name is Melker, and I come from Nyköping, and I have a question to Hel. Well, I was just wondering how you isolated the molecules and just turning on a single molecule instead of, well, more. How did you manage to do that?
How do you isolate a single molecule? But usually what you do is you make sure that there's only one molecule capable of emitting light. So in this last concept, what is usually done is you have a molecule that can undergo a cis-trans isomerization, for example. Say in the cis case, it emits light. In the trans case, it produces the absorbed light into heat. It converts the absorbed light into heat. And then it's dark. It appears dark, although it's illuminated with light. That's one option. Or there's many ways. You can also associate and dissociate molecules. And if it's on, attached to something, it's on. If it's dissociating and running around, it's off. And then in that way, you can generate an on-off contrast. So there are many ways of doing it. In the stat case, of course, the on-off contrast is produced just by an optical transition, which is the most fundamental way of doing it. This is also why this was first, because this is the first thing you think about if you really want to turn a molecule off. There are several ways of doing it. And of course, this plays a role in practice, because the way the on-off is done, of course, has an influence on the performance in practice. But there are several variants. Maybe there's even more variants that have been described, and that may, of course, have a big impact on the actual practicality.
Okay, thank you.
Hi, my name is Michelle Silberstein, and I'm from Stockholm, and I have a question for Professor Törma. And I was wondering how you can know when the BC state is reached, seeing as in your experiments, the state only lasts for less than a picosecond. So what I'm asking is how you record your results.
Yeah, so we record the light that comes from the sample, and we measure several things from it. For instance, we measure how much photons we have at a certain energy, and then we can fit that distribution to the Bose-Einstein distribution, for instance. And we do the experiment several times so that we first excite with a small amount of pump, so give small amount, and then we don't see anything. We give a bit more energy, we don't see anything, and then when we have reached the threshold, so to speak, we suddenly see the distribution going like this. And this distribution is just one indicator. Then we can look at other things, for instance, how much spatial coherence there is. And this behaves in the same way, that first there is less coherence, and then when we reach the BC, there is more.
Okay, thank you.
Hi, my name is Samuel. I'm from Stockholm. I have a question for you, Professor Hell, and that is, you said that the resolution that you've just reached, 1 nanometer, is around 1 nanometer. Is there? You said that there wouldn't be any higher resolution, at least for now. Is there any interest to actually go even deeper?
Yeah, I mean, the limitation of fluorescence imaging, and this has been just fluorescence image, is the fact that you image the fluorescent molecules. And nothing else, just the fluorescent molecules. And once you have identified each molecule you're at the end. There's not more you can do. In essence, what you do is, of course, you separate molecules that are very close to each other, and the smallest entity of separation is the molecule itself. And this is why there's no way to getting further within the concept of fluorescence microscopy. So that's why I'm saying it has reached the limit. Of course, if you manage to get rid of this fluorescent labeling and find a way to overcome the diffraction barrier without the need of having, say, fluorescent labeling or the specific states that are used in fluorescent labeling, then, of course, you may get further. But no one has found a solution yet that deserves mentioning, put it that way. Okay. There are all kinds of concepts around, but none of them really worked. I mean, but maybe you've come up with something that would be something, and in my view, this is just my humble view, if somebody came up with a light microscope that breaks the diffraction barrier in the scattering reflection mode by factor, and you get down by a factor of 10, it would be a Nobel Prize, in my view. But no one has come up with something that really works.
Okay. Thank you very much.
Hey, Yahoo. My name is Alexandra. I was up here before. I'm from Lidköping. Heja huvudjulloa. Guess who my questions are for? Okay, so plasma is a superconductor due to the plasmatic potentials. These are, however, the fourth aggregation state of matter. And how come plasma has so very similar properties to Bose-Einstein concentrate when they are like at the opposite sides of the spectrum of heat?
So are you asking how can we have a plasmonic Bose-Einstein condensate, or?
Yes, what is the correlation between Einstein-Bose concentrate and plasma, because they are so very different in temperature?
Yes, so yeah, in our Bose-Einstein condensate, this plasma part is just that the objects that we condense, they are mostly light, but they are also plasma oscillations of electrons in the nanoparticles. And this whole object, which is like, let's say, 90% light and a little bit of plasma oscillation, this is a boson, in the same way that some atoms are bosons or photons are bosons, and it can condense. So anything that, any kind of a particle or quasi-particle, this kind of hybrid particle, which is a boson, can undergo Bose-Einstein condensation in some conditions.
Okay, but is Einstein-Bose concentrate, does that have similar properties to plasma in that there are bosons?
No.
I think the question is about plasma, not plasmon.
Yeah, okay, plasma. Well, I would say that the properties in general are very different, because if you think about just plasmas, like in a tokamak or something, this is extremely high energy and very strongly interacting system. But
it's fermionic, isn't it?
Yeah, I mean, it's formed of fermionic particles that have charge and so on. It's very far from Bose-Einstein condensate.
Okay, thank you.
Hi, my name is Edip. I am from Kristianstad. So this question is to Professor Turle. So I know you feel the study isn't really string theory, but there are of course a lot of discussions, just theory of everything. So which theory would you consider to be most successful, string theory or quantum theory?
Oh, wow. Yeah, now that I go to pure speculation, because I know almost nothing about string theory, but it's true that quantum theory cannot explain everything, so it's not complete in the sense that there is no elegant, good theory that can combine gravitational phenomena and quantum phenomena, for instance. And if we go to some extremely small length scales or huge masses and so on, we don't know whether quantum theory works at all. So I wouldn't put them like in comparison to each other. I mean, quantum theory is something that we know it works really well for many things, but we know it's not complete. And string theory is just one guess of what could be a better theory.
So the other question was, the Large Hadron Collider that was in the presentation. Can you not use that collider and use laser beams to measure black hole waves?
Sorry, can you repeat?
The Large Hadron Collider that was on the presentation. Large Hadron Collider was on the background.
Yes, yeah.
So I was thinking, can you not use that collider and use laser beams to measure black hole waves?
Well, this I don't know. I mean, that collider was there. The only connection to my talk was that they use superconducting magnets for accelerating the beam, so I actually am not expert enough to answer your question.
Hi, my name is Jacob and I'm from Halmstad, and I have a question for you, Hel. What is that holding this technology back from seeing even smaller things? What's the bottleneck?
The bottleneck is the labeling in the end. So, as I said, the bottleneck is, can you get a fluorescent molecule to the protein that you want to see in life science imaging? And because in the fluorescent microscope you see nothing but the fluorescent molecules, nothing else. And you infer from the fluorescent molecules on the actual thing that you want to see. And of course the attachment usually goes via linker in many cases. And so there is a distance between the fluorophore and the actual, say, protein that you see that could be 2-3 nanometers, 1 nanometer. Sometimes you can attach the fluorophore directly, and then it's fine. But sometimes there is a distance, and this is the real limitation that there is now. So even if we manage to see all the fluorophores exactly at the same position, at the correct position, which we do by now, there is this limitation of labeling, which has nothing to do with the development of microscopes. We've done our job. As physicists or chemists, we've done our job, full stop. It's now, as I said, up to chemists, real chemists, to really sort out that problem, because that will, in the end, determine what can be seen and what the fidelity is and so on. But this will be sorted out because it's not fundamental. But this is the actual limit.
So you could use your technology to see even smaller things if others come up with ideas to see other things.
I mean, you can see, for example, the organization of DNA in the nucleus, if you manage to label DNA. You could see the distribution of proteins, say, in anything that you can measure, on a vesicle, for example, which is extremely important. No one has been succeeding in doing that, and electron microscopy doesn't work for it. Because electron microscopy lacks the specificity of molecular labeling, so you cannot do it really. And so this is the strength of fluorescence, that you can really specifically get to the proteins or the other biomolecules that you want to see. And there's a huge range of applications out there, I have no doubt. It's a huge playground that is open now. And there will be many discoveries as a result of the high resolution. It's so obvious, because it's not just by a factor of 3, 4, so a factor of, say, 10 to 100 really makes a difference, and especially in 3D, and especially if it's done in a live cell. So I have no doubt that new chapters will be opened in the life sciences as a result of this progress that has been made in fluorescence imaging. But you shouldn't, as a physicist, you might think, okay, going into smaller scales. For fluorescence, there's no point, in my view. But there is a huge range of applications between, say, 1-2 nanometers to 100 nanometers in biology that is totally uncharted. And there's many things to be discovered.
Thank you.
Hi, I'm Helen from Sweden. I would like to direct my question to Tomai. Gosh, I can't pronounce. Sorry, I'm very bad with names. And I was just asking about this band edge. I'm not sure if I missed it in the presentation, but what is the band edge?
What is the
band edge?
Band edge, okay. This is when we have these energy bands, they have some width, so they are from some lower energy to some higher energy. This is the width of the band, and band edge is the lowest point. It can be also the highest point. Yeah, I didn't explain it. So it's the lowest energy of the band.
Only lowest?
Sorry?
Was it only the lowest band?
Yeah, in our case it was the lowest, because we want to form the Bose condensate there, so it has to be the lowest energy.
Thank you for your presentation.
Mm-hmm.
Hi, my name is Johanna from Gymnasiet, and my question is also for Professor Thurmer. You said that graphene was the best material for creating the flat bonds. What makes that a good choice?
Yeah, so actually flat bands you can do with many systems. They have been done in various different systems, but this graphene is now the only place where they have shown that there is superconductivity in a system which also shows flat bands. And yeah, why this flat bands form is because they have actually two graphene layers on top of each other. And they are somehow connected so that the electrons can tunnel from one layer to another. And therefore, the energy bands of these two layers, they also interact in such a way that at some point they become flat. So that's a very nice way of forming these flat bands in a controlled way. And actually, then they show superconductivity there, which is quite actually surprising.
Thank you.
Hello, I'm Axel from Polhemsgymnasiet in Gothenburg, and I have a question for Professor Hell. So with this new high resolution, are there any molecules in particular that you want to look into more? For example, is this the first time that you're able to see just one single DNA strand in the cell?
Yeah, it's a good question. So personally, if you ask my personal motivation, to be honest with you, the whole thing, addressing this problem resolution, I did out of curiosity. I wanted to know if there's physics that allows you to get better images. And if I had a good idea that would have done it for reflection imaging, I would have done it. I didn't care about life sciences. My motivation was not to do something for the life sciences, not at all, being a physicist. So even now, right now, at this point, I'm not driven by applications. So all the applications that are taking place, it's done by collaboration, by talking to people, they expressing interest. I'm trying to help them and trying to figure out if this is reasonable or not. So I'm personally not, I wouldn't even call myself a microscopist because I'm not. I'm not the type of person that looks into microscopes all day. This is ridiculous. I want to sort out a problem, and this is done in a different way by thinking about what the challenge is. So this is something I want to convey to you. So I'm the wrong person to ask this question. But if you ask me what is now interesting that should be looked at, I think, for example, the synapse in the brain. And so this is, I must say, having said this is something that I really find fascinating because we know that with this method, not only we can see this in cells, we can also most likely work it out in a functioning brain, in a mammal. Not deep down, but in the upper cell surface. And seeing perhaps something going on straight in the synapse, a molecular change. I think this is viable. It's still cutting edge, and you have to work out a number of things, but viable, and I think in the end will be done. And that's something that really fascinates me. And that may come or may not come, but I think it will come in the end.
Thank you.
Hi, my name is Hemming, and I come from Norrköping. I firstly had the same question as the guy before me, but I want to ask you, Hel, about how did you first came up with the idea of this solution to get a better accuracy?
I was just fascinated by the idea, more or less out of misery. I was asked in my PhD student time to look into the use, not functioning, the use of confocal microscopy, laser scanning confocal microscopy for the application of computer chips, which is the least scientific project you can imagine in physics, perhaps, because there was no physics in it. And I got so bored, and not only bored, also distressed by the fact that it didn't contain a real physics problem. It was so technical. I got computer chips from Siemens and IBM, and I had to measure the line width on the computer chips. It's terrible. And so I felt, okay, why did I do this? Why did I opt for this boring, say, physics of the 19th century? And I was just about to become depressed. I really mean it. And I thought to myself, okay, maybe there's still something interesting that could be done with this, say, boring physics of the 19th century. And then I figured it must be the diffraction barrier, breaking the diffraction barrier. That's cool. That's something that is really cool. I decided to look into this problem out of fascination. And the reason why I felt it's not as crazy as it seemed to the people at that time was that I knew that a lot of physics has happened in the interim since the diffraction barrier was found, since 1873, that there must be something. Say a quantum phenomenon, I looked into, say, non-classical optical phenomena, I looked into all kinds of nonlinear optics phenomena. Of course, I was a child of my time and so on. I looked, of course, into molecular transitions. And the new quantum mechanics was invented. There must be molecular transitions, laser was invented. So I screened textbooks in order to find the phenomenon that allows me to overcome the diffraction barrier. So this really, it was that broad. And I couldn't find something for reflection. And then I realized, oh, but for fluorescence it may work, because there's molecules in their states. And if you ask me what my real discovery was, I realized that if you play with the states of the fluorescent molecules, you may get across the diffraction barrier. That was the actual discovery. And I knew that before I came up with the concrete stat concept. I knew if there is a way to go, it's going about the states of the fluorescent molecule, and for fluorescence it may work. At that time, I didn't even know that fluorescence is important for the life sciences. And then later I found out, I'm very serious about it, later, a couple of years I found out, oh, this is important for life sciences. Lucky me. Lucky me. It may become really important. Yeah. But this was not my motivation.
Okay. But did you have many failures by...
Sure.
Yeah.
Sure. So when I realized that maybe STAT is the way to go, and the first one was very excited. Oh, this could lead to something, and this may be a way to go. Then I remember it was on a Saturday morning. I realized, oh, this could be the way to go. Then in the evening, I said, maybe it's still wrong. And the next day, I woke up, maybe it's wrong. And then it went like this for a couple of days, of course, where I struggled with myself. Is this wrong or right? Is this wrong or right? Is this going to not work for some reason? And then in the end, I figured out it should work. Of course, you never know until it's done.
Okay.
But of course, and there have many setbacks and a lot of discouragement, because those people to whom I explained the thing, they said it's not going to work because. And I was courageous to believe that it works because I didn't know all the limitations that these people were talking about. Mm-hmm. So not knowing and being courageous, and this happens if you're young, of course, is a big advantage. So you shouldn't think that if you know everything, the chance of discovering something is large. Mm-hmm. Not true. It's better to be, at times, to be ignorant. Have enough knowledge to be creative, but also have enough ignorance to be courageous.
Thank you, Professor Zell. Thank you.
Hello, my name is Victor from Fagersta Brinellskolan, and my question is directed to Stefan Hell. And I wanted to ask, since you said that you've reached the limit of your previous work, my question is, how is the future looking for you in science?
Yeah, well, I'm asking this question myself too, so it's a very good question. So every morning when I wake up, I'm asking, so what I'm going to do now? I'm speaking the same thing I've been spoken about for the last couple of years, or 10 years, a decade. No, it's a good question. Yeah, so of course, you can always find something. Like here, of course, you can do this better. And there will be improvement on this, and they will have an impact, and the biologists will like it. It'll become faster, it'll become brighter, it'll become, I don't know what, easier to use. But you are right. Conceptually, probably, I'm not saying for sure, but probably it won't be a big difference. And of course, this puts me in a situation where I have to think, okay, where do I see myself? Just pushing this? And having it, say, disseminate, or going to something that is, say, more applied, like checking out the synapse, for example, that would be interesting, or doing something else. And so I've not decided yet. But maybe if I happen to be invited in a couple of years, I may be able to give you the answer.
Thank you.
2 more questions.
Hi, I'm Abdullah, and I'm from Stockholm. My question is directed to you, Professor Hell. In nanoscopy, what is the effect of the molecule's temperature on the grade of the resolution?
This is all done at room temperature, fortunately. Of course, the molecules can move, that's clear. And if they move, of course, there is a certain window of time in which you can locate them. If they move very quick, you cannot locate them anymore. But this new method, as I said, because it requires fewer fluorescence emissions, can be 10 times faster, 50 times faster than what is usually done, even 100 times. So this will be improved further. So in that sense, movement due to, say, Brownian motion or whatever it's going to take place in the cell, of course, can be much better captured than normally. And it's the best way of doing it, right, that I'm aware of now. But fortunately, everything works at room temperature. This is really good.
Because cooling down molecules to 0 Kelvin, not 0, but like close to 0 Kelvin, usually slows the slow searching, so it's easier to capture the molecules. So would that improve the resolution?
Yeah. You could go to lower temperatures. This has positive and negative effects. Positive effect, it's frozen in. The bleaching of the molecules is usually reduced of the fluorophores. There's downsides. At room temperature, you find the molecule go to a long-lasting off state, and you cannot get it back that easily. That's a serious downside. So you cannot control the on-off that well. But it may work under certain circumstances. So there are groups that do that. There's kind of developing light microscopes that work at low temperatures, usually nitrogen. And there will be advantages to that, I have no doubt. But personally, I don't find it that appealing, me, personally. But who knows? It may lead to something that is practically important.
Thank you.
Last question.
Hello, my name is Valentin Hassan. I'm from Uppsala, and I'm addressing this question to you, Dr. Helm. I was just wondering why the quadratic function appears in this approximation of the molecule's position.
I mean, if you have a 0 in first approximation...
But why this measurement follows a quadratic function?
Your field changes sign, and you square the field, and then, of course, you pass a 0. And then it's a quadratic function.
Okay. Is there anything you would like to ask each other?
No.
Okay, so we thank the speakers and we thank the audience, especially the active asking questions audience. I think it was terrific. And now we change to the next topic.
So I have the honor. I'm going to share the third and last session for this first day. We have two excellent speakers, one terrific now and one after the coffee break. We will start with Thomas Ebbesen, and then after a short break, a 30-minute break, we will have Jennifer Dion telling us about different stuff. So Thomas, who is now entering the stage, is actually from Norway. Was born in Norway, but educated in France and in the US. He is a physical chemist. Doesn't tell you much, I guess, but that's the chemistry which is between chemistry and physics. Thomas has, if not coined, at least discussed something called strong light matter coupling for the last 15 years or so, a field that has grown tremendously the last 5 years or so. I think his title of the talk is The Alchemy of Vacuum, so I'm very interested to hear what that means. Probably that there are strong light matter interactions in the absence of light. So I hope that's what you're going to talk about. So with that, I think I'm going to just immediately leave over the word to Thomas. So please.
Well, thank you very much. Thank you for the organizers for this unusual event. I've never been speaking to so many high school students in my life. And I've spoken at Rotary clubs many times, but not for students. And I unlike you, I want to start by saying that when I was a student, I wouldn't have understood anything of everything. When I was a high school student, anything that you've heard so far. Okay? I'm impressed with your questions, really. And I was a mediocre student, as you can imagine. So I'm going to talk about something that you probably have never heard about, and including the scientists in the room, except for those who work in this subject, and who are more physics-oriented. This is about light-matter interactions as seen in quantum electrodynamics, another version of quantum physics. So I'll come into that in a second. And the reason for my title is because there was so much skepticism about when we published the first paper about 7 or 8 years ago. We demonstrated some changes I'll talk about in a second, that I essentially, a colleague of mine just said, why don't you just call it alchemy since nobody believes it? So this is what it's about. So I'm going to take you a little journey, and to explain what I'm doing, I have to go through a path. And I'm not going to come to what I want to say until quite far into my talk. So light-matter interactions are ubiquitous around us. We are talking to each other, we can see each other, the light, the projector, everywhere in our life, telecom, everything you're using, your smartphone, everything that the internet uses light-matter interactions. They're so much around us that we don't even think about it. The light comes through your lens, switches a molecule, like in this photoisomerization. It happens in about 200 femtosecond or something like that, and it switches, and you get this mechanical, physical change, essentially an optomechanical event, which triggers a change in your membrane, and this gives you an image eventually in your further up. Light-matter interactions, of course, essentially in the biosphere. We wouldn't be here, especially in this part of the world. And I come from this part of the world too. I spent my youth playing in the granite north on the coast here when I was very young. So these are in here. There are lots of interesting events going, physical chemistry phenomena that go on, and I'll come back to that later on. But they're absolutely essential for us, for existence. But what is more, and everybody knows this, but most people don't. Oh yeah, so here, sorry, I forgot about this. I wanted to introduce states, but Päivi before introduced molecular states. It's very important. Everything I'm going to talk about is that molecules have different energy levels. You know that, and probably you all know that. I didn't know that when I was in high school, so I put this up. And these are electronic states, and then there are sub-level vibrational states that superimpose and gives rise to these broad peaks for chlorophyll, which gives rise to the green absorption. So light is absorbed by a molecule like in your eye or in a plant. At the level of the molecule, one photon is a huge amount of energy. Okay, huge. You can make a little calculation to estimate what that is, and so it gives rise to new chemistry and all kinds of other interesting events, which is then stored by the plant. What is much more or much less obvious is the fact that even in a droplet like this, there's light-matter interaction. And I, as a physical chemist, as pointed out, somewhere between physics and chemistry, you never learn this. Actually, no chemists learn this. Physicists learn this, but chemists don't. And even in the dark, there are light-matter interactions. So how can there be light-matter interactions in the dark? And that's where most people start getting a bit lost. And so then I have to bring you back to some history. To understand that, you have to look into history of our understanding of vacuum. So vacuum, the discussion about vacuum has been going on for thousands of years. In the Western world, it's Aristotle and Democritus is one who gave us atoms, notions of atoms. They didn't disagree on this. Aristotle thought there was no such thing as vacuum. Democritus thought there had to be some, because otherwise there had to be space between the molecules, for example, for things to mix, like sugar in water or a dye dissolving again in water. And in this debate, however, Aristotle's views was the view that was held in the Middle Ages in Europe until the beginning in the sort of 17th century. And then people started doing modern science, and they had vacuum pumps. This is kind of surprising. Actually, vacuum pumps had existed for far longer than that, but they started doing modern experiments. And there were three people, Italian, German, von Guericke, and Blaise Pascal in France, who actually made vacuum in different ways, and in different systems. The most famous one is the von Guericke one, done in Germany, where he took 2 half spheres of metal with a liner, pumped it, probably with a hand pump, and he went in a village, and he couldn't, nobody could separate the 2 half spheres, and then he let air in, and he could separate them. And this looked like magic. So he had to then repeat it in front of the king or the local prince, and this is sort of the Instagram from 1654 of this event. Here you have the 2 half spheres, 8 horses on both sides trying to pull this sphere apart. They can't do it, and then he opens the thing, he lets air in, and it works. He can separate them. But that was a big public type of thing, but Torricelli and Blaise Pascal their experiments perturbed the scientists. Why? Because they did vacuum in glassware. And one of the things that perturbed them was the fact that light went through what they thought was empty. Of course, it wasn't totally empty. They weren't very good vacuum pumps, but they thought they were empty. And so there was no matter inside or nothing inside, and light still traveled through this glassware. And this was perturbing because they thought there was a medium. The light had to travel in a medium. And so people like Huygens, Newton, they sort of had to grudgingly accept that there were something called ether, something that remained, an unknown substance that remained after the vacuum was pulled on these systems. And that actually survived through Maxwell's equations, which is kind of amazing to me. And until Einstein came around and came with relativity, general relativity, and then suddenly vacuum was just, now we are changing the meaning of vacuum here. Here I'm switching over. Vacuum is now just space, 3-dimensional space, and that 3-dimensional space had nothing in it, and light traveled in that 3-dimensional space, and light followed the curvature of the gravitation of how space was curved by gravity and so forth, but there was nothing else in there. And this new version of space, which lasted only about 20 years, because then people tried to quantify fields. Okay, and this, with Dirac, tried to quantify things, how things interacted at the distance. So, for example, ask yourself, how does a positive charge know the existence of a positive charge a nanometer away, 10 nanometers away, or it's a negative charge? How do they? Okay, that you can ask me afterwards. I won't answer the question now. Okay, but these are the kind of questions that they were asking themselves, and out of this came quantum electrodynamics. It's much more complicated than what I'm showing you, explaining you now. And in this notion of quantum electrodynamics, vacuum, meaning space, is full of activity. Particles are being formed, disappearing moment in a sort of temporary way. And that's how, and this fills space everywhere in the universe, including here. In your head, in your brain, in my hand, everywhere. So there are many types of fluctuations. There are things related to particles, and I'm more interested in the electromagnetic part. So, but just to show you how much is going on in between in the space, if you empty even out in the universe, if you look at the speed of light, just look at the speed of light. This comes from Maxwell. It's inversely proportional to the dielectric constant of vacuum. It's called permittivity, but you might as well call it dielectric constant, and permeability, the magnetic response. You can see the speed of light that vacuum, meaning space, has a dielectric constant. How can nothingness have a dielectric constant? You already see a problem right away. Okay? It has a magnetic response too. These actually is the drag on how when light travels through space, it gets slowed down. It's like walking in water or something on a beach. And the interesting thing is that it's very close to that of glass. So if you read books on this, which I have done to try to understand all this, you realize that actually contemporary quantum field theoreticians think, or at least some of them think of vacuum as a dielectric, meaning a non-metal. Okay? Like that you can manipulate. So, now I'm going to just talk about the vacuum electromagnetic fields. I learned a few years ago that there were various kinds of vacuum fields, and I'm just going to talk about the vacuum one. So what, in QED, light is treated the same way as matter. So light doesn't just come out of a lamp, out of these lamps up here on the projector. It actually goes from a state in matter to a state in vacuum, in space, essentially. I mean, I'm not meaning material vacuum anymore. There's no more material vacuum in any of what I'm going to talk about. Now I'm sort of a physics meaning of vacuum. And so it turns out that space has because it's infinitely big, has an infinite number of such states. And that's where the bosons go. Like there can be many in one state, as you know. We heard this from Päivi Törmä. And all these states have Heisenberg's uncertainty principle attached to them, so they fluctuate. And this gives rise to background fluctuations everywhere. Okay, absolutely everywhere. And they impact chemistry in a big time, and this has not been understood, and that's where we come into the picture. So, here's some representation of such fluctuations from an Australian website that I found. These fluctuations are now detected because sometimes I have people, physicists, come to me and say, no, there's no such thing as vacuum fluctuations. Well, they are now observed experimentally. There are two papers, one from Constance and from ETH, which shows that indeed you can catch them. You can see them. They play a role in chemistry. I learned all this about van der Waals forces. When you're a physical chemist, that's one of the things you learn. And you learn that there are fluctuating dipoles that gives rise to London dispersion forces. But as you can, the question is, where does the fluctuating dipole come from? Well, it comes from the fluctuating electromagnetic fields that are everywhere. And these are not negligible forces. So the forces are so strong that if our hands were it holds my skin together, or your skin together. So if our hands were totally flat and I shook Stefan Hell's hand or somebody like that, they have very smooth hands, we shook our hand, we need surgery to separate us. So you're glad your hands are not so smooth. And you don't shake hands like in France, or like we do in France. Anyway, so that's where light-matter interaction plays a role, even in such a thing inside a droplet. And so you can imagine that you could put a droplet inside a cavity and isolate it from the universe. You can do that already. You can stop molecules from fluorescing, for example. Things like quantum yield of fluorescence, which I was told is something inherent quantum yield, inherent lifetime, those are not inherent. It depends on the availability of these states around us and everything, availability of the states for the light to go into. So I'm not going to talk about the weak coupling, but that plays a big role. I'm going to go switch to strong coupling, because in half an hour I don't have time to do that. So physicists look at light-matter strong coupling in two regimes, weak and strong. Weak, you modify radiative properties of light coming out of an emitter, for example. And in the strong coupling, the interaction is so strong that you have new energy levels in the material. And the way to understand this is to look at coupled oscillators. So coupled oscillators was understood by Huygens. We heard about Huygens already today, the pendula clocks. He invented that. And in his time, in 1650, this was a revolution. This was serious. This is like the GPS of today, okay? The atomic clock today. It was the first time that you got fairly precise time, which saved considerable amount of lives and ships and so forth, because you could determine your position more precisely. And he, when he was making this, he must have had more than one, because he noticed that the clocks got synchronized, and he wondered why. And he solved the coupled oscillator model shown here. And here's a modern YouTube version. I'm going to show you with 5 metronomes. Everybody knows here what a metronome is for music, to set a beat, regular beat. And so here's 5 metronomes out of sync. And this should have sound, I hope. Oops. It's always like, what? Don't tell me today. Sorry. You can hear and see everything at the same time.
No, I'll move it back.
Okay, I did this in a music store. The guy thought I was doing magic, okay? This is the magic of science. So, you see they're all synchronized, they're all moving together. How they do that? So they are actually exchanging energy, and that's why they need to be on those empty beer cans, because they have to, they give each other a kick, and they go into a new ground state, they synchronize and go into a new ground state, just like here. This is very similar to H plus H forms H2, and you get two orbitals. I mean, if you're a chemist, that's a very, very similar analogy. So here, when they want these new states, you can do it turns out you can do absolutely the same thing with light and matter. So you can couple an optical resonance of anything. It can be a surface plasma, as we heard about, a cavity resonance, with a material resonance. As long as they're at the same frequency or same wavelength, on the right conditions, they will start talking with each other. Instead of exchanging mechanical energy, here they will exchange virtual photons. So a molecule, even the transition dipole moment of a molecule that gives rise to the color, that gives rise to the transition from one state to another, fluctuates. They all fluctuate. A cavity also fluctuates, even in the dark. And so they can interact here. These are virtual photons. Don't ask me what that is. Maybe you can ask some of the quantum physicists in the room what they are. Anyway, they exchange photons, and they give rise to new states. These are exactly the same principle as making J gates. We talked about J gates before. That's how J gates are used. I have a slide with J gates. I took it out because I don't have time to go through that. But J gates talk to each other. The transition dipole moments are aligned and talk to each other and give new hybrid states. The crazy thing here, and that's where most, at least chemists and even physicists, sort of blank out, they're hybrid light matter states. So now you have a wave function that has a photon content, electronic content, and it's hybridized, and you can give rise to hybrid light matter states and hybrid light matter particles, sort of quasi-bosons, quasi-fermions, whatever you want to call it. And how do you do this experiment? So I skip all the theory. So how do you do the experiment? So it's very simple. Conceptually it's hard, but experiment is very simple. You take a glass slide, evaporate 20 nanometers of silver or gold, spin coat molecules on top, come with a second mirror, and make sure that layer of molecules is just thick enough that the cavity resonates, has an optical resonance, same frequency as the molecules. And then, like here, and then this cavity here is tuned to this molecule here, and then you get two new absorption peaks. And if you're a chemist, this means a new molecule. Okay? The thing is that most of the physicists who worked on light matter strong coupling worried about the optics. For me, I was stimulated in doing this because I read an article on cavity quantum electrodynamics 30 years ago, and I wondered what it did to matter. And what essentially you have is you have to go from here to here by synthesis would take 6 months of research. Here you just close the cavity, and you get this. You can remove it, and it goes back to the original state. And if you have a system like that, it has to be different. It has to have different properties. This is obvious to any chemist, but the problem is that chemists don't know QED, and I'm just at the interface, and that's where I come in. So the other thing that is important to understand in what I'm going to say is just like there are 5 metronomes in the other thing, coupling, all moving together. In our cavity system, the optical modes are roughly in the visible are roughly micrometer cubed. Molecules is a nanometer cubed. So you can pack a lot of molecules into the cavity. And from a quantum mechanical point of view, you have to sum over all the possibilities. One cavity mode can interact with 100,000 different molecules. Then you normalize and do all kinds of little tricks, and you end up with a very large collective splitting. You get instead of 5 metronomes, you have 100,000 metronomes, all doing this. So all the molecules, electron clouds, all the molecules are oscillating. And we know this because there have been experiments done, including in Pavy's lab, where you see coherent emission from molecules far apart, micrometers apart. And the crazy thing about this is that when you keep on adding molecules to the cavity, the electronic structure of each molecule changes. First you get these collective states, which are interesting from transport, conductivity, and so forth, but you also get that all the gaps are changing. That's as if people came into this room, people started leaving, we got smaller and smaller and smaller. Once they remained, people came into the room, we started getting bigger and bigger and bigger again. It's kind of weird. And this is, real. This is not just we see this in experiments. So you start off with a molecule like this. You end up, I've just shown 3 states, the ground state and two excited states. Here, if you switch from that to that, as I said before, you don't have to excite the material. Just the fact that you change the eigenstates of the material changes the properties. That's exactly what Päivi was saying before. It's the electronic structure which determines all properties, whether you occupy them or not. And so it's pretty obvious that they should change. So we have looked at a number of things, and I'm just going to talk about material properties and molecular and chemistry. And I've chosen to talk about chemistry. So chemical landscapes are not these simple bars that I showed you before. Those are representation of actually landscapes of potential energy surface that are very complex. And here's an example for this isomerization reaction. There's a ground state barrier here. Generally, when you learn this in school, you just see a little barrier between reactants and products. But in excited state, it could be reverse. You can spontaneously isomerize. That's what happens in your eye. And so another thing that's very important in molecules is that you have all these vibrational modes. And they play a huge role. So in a typical molecule, like the ones I'm showing here, there are probably 100 vibrational normal modes. So they play a role also, of course, in chemical reactivity. So when we first did the experiment, the first proof that you could modify properties on the light-matter-strong coupling, non-optical properties, just a property, a basic property of the material, was an experiment we did in 2010. It took a couple of years to publish it. And we showed that the photochemistry of the excited state was modified. This was the paper that gave the word alchemy, because the first time in my life I got a referee report that said, this is not science, this is science fiction, reject. It's the shortest also referee report I've ever gotten. And this the editor, of course, believed. Luckily, eventually Angewandte Chemie published this paper, and since that we moved on. In this paper, we speculated that while the excited state is interesting, it would be much more interesting to look at ground state chemistry and just couple a vibration. But the vibration is tiny in energy. The energy of vibration modes is tiny, 1/10 or at least of an electronic transition. So would that really perturb anything? We had no idea. It turns out it has a huge effect, way beyond what we imagine and way beyond our understanding. So to do this, we had to switch now to cavities in micro. The advantage of working in the IR, the vibrational bands of a molecule are at typically 10 microns. And so we are in the infrared, therefore we can use cavities that are 10 microns thick, and we can do microfluidics. We can have liquids inside between 2 plates and just follow the chemistry between 2 plates in the dark. Okay, very important, in the dark. There's no vacuum and there's no light. Okay? And so for that, we developed a system. I'll show you in a second a photo of what we did. So we did chemistry. So we have the mirrors that are infrared transparent. We put some gold or silver. But we quickly realized that chemical reactions ate the mirrors. So we had to put glass. So we put glass, 200 nanometers of glass, to protect the mirrors from the chemistry. So the first reaction we did is very simple. So here you have this cut of a potential energy surface of a molecule, and this vibrational ladder. You split it with a cavity mode, and we looked at this carbon-silicon deprotection reaction, where this fluorine here tacks this carbon-silicon bond and breaks it. Don't ask. I'm not a synthetic chemist at all, so don't ask me any questions about this. We do this through collaborations. And this is a very, very simple reaction that fit it was a proof of principle reaction. When we did this, here are the cavity modes in red. Here's the absorption of the vibrational modes of the molecule. And this peak here is the carbon-silicon vibrational stretching mode. It's going like this all the time, okay? And it has 0-point energy, so it's vibrating all the time, okay? Yeah. So, when you do this, when you tune the cavity and you hit this, you split this vibrational mode into 2, you go from having a rate here outside the cavity or off resonance to a much slower rate, a slow down a factor of 5. Of course, my postdocs and students were very disappointed because they want fast reactions. We live in a fast world and everything has to be faster. But then they looked at the thermodynamics. And I'm sorry for you, if you, those of you who had not done, I thought of going into thermodynamics. We had some introduction to thermodynamics today. This is classical thermodynamics, macroscopic. But from the thermodynamics of the reaction, you can actually, doing a temperature study of the reaction, you can determine the enthalpy and entropy of the reaction. I'm not going to go into the details. But what's very surprising here is that they change dramatically. The enthalpy doubles, the entropy changes sign. And this is huge. The splitting we have is less than room temperature in energy. And we have 10 times more bigger changes in the thermodynamic parameters. It's very surprising. And to my collaborators, this is a proof of a change in reaction mechanism. The carbon-silicon bond starts breaking before the fluorine attacks the bond. So this was a big surprise to us, and then we decided to go look at other things. So the next thing we decided to target is if we can tilt the landscape just by coupling vibrations. So our collaborator, who's a synthetic chemist, Joseph Moran, prepared a molecule with 2 leaving groups, and so 2 transition states, and with roughly equal proportion of giving yield of one product and the other. And then we want to see if we can tilt the landscape and change the yield, because that's absolutely central for pharmaceutical industry and for all chemical industry. There are some drugs that are not on the market because they're too expensive, they're too impure when they're made. If you're not chemists in the audience, this is important to understand. It's absolutely critical to steer a reaction to the yield, to the product you want, to bring the cost down and the purity up. And so this was a proof of principle, and when we did this, to our great surprise, yes, we can invert the yields. We could start with 60% of one and end up with 20% of one and go 40 of two and to 80% of two. That was a huge surprise to us. But what's even more exciting to most people is this, what we call an action spectra. So what we do is, this is contrary to Emmanuel Bloch's table full of very complicated optics. This looks like this. This is our optical table. Here's our cavity, and with a screwdriver we tune the whole thing, and it's a sort of a 10-euro experiment, and we tune it across by squashing a little. We have a little spacer made of a polymer, so it's squishable, and we just tune the cavity by squishing this spacer. So when you do this, you can tune across all the vibrational bands of the molecule, and you find that only 3 are involved. Okay? And so this is a mechanistic tool without injecting any light. I repeat, there's no light, because people still come to my lab and think we're injecting light into the experiment. Okay? There's no light involved in these experiments, except when we take the spectrum, and you can see that only these 3 vibrations, and I'm not going to go into details, but they make sense. But I can tell you now that there are systems we are studying now, which will be for next time or in the future, where you don't expect any vibrations to play any role, and you see a huge effect of vibrations. And in chemistry, there's something called Born-Oppenheimer approximation, where you separate the vibrational part from the electronic part. Well, clearly, you cannot do this as much as we thought. And that's fascinating. So, and we have, okay, if anybody wants to do, if anybody wants to do this experiment, we have a video online, so it's more accessible to people. It's very easy to do. So then we wanted, of course, to do catalysis. And one of the problems with this approach this strong coupling approach to modifying chemistry is that you need high concentration. Why? Because you need to have high absorption to exchange photons, virtual photons, very fast with a cavity in the dark. And one of the dreams have been that we cannot always work with high concentration of reactants. So can we couple, for example, the solvent, which is always high concentration, and transfer that strong coupling to the solute? From a quantum mechanical point of view, this is not possible, strictly, because then even if they have the same frequency, they vibrate at the same frequency, they are not identical, so you cannot do this permutation and look at all the equivalent permutations. It turns out it is, however, possible. You never give up. This is what Stefan Hell was saying before. You should, even if you think something is impossible, it's good to be a bit ignorant, because then you try things which textbooks say it's not possible. So what we did here was we looked at this reaction here, and we coupled this solvent has the same motif, this CO carbonyl stretch here, this carbonyl, COH, and this ethyl acetate, and so they have the same, they vibrate at the same frequency, and we want to see if we could affect this reaction. And then not only could we affect it, but we could catalyze the reaction. Okay, we can accelerate the reaction by an order of magnitude without a catalyst. Okay, you have to understand that we wouldn't be here if there were no catalysis. Okay, there wouldn't be enough food for us. Okay, on this earth. We'd be a smaller population, have less problems, but there would be far fewer of us here. So, catalyst is the basis for all the material science, all the way from pharmaceuticals to chemicals to materials, okay, to fertilizer. And so, catalysis is very important. And here you see this huge acceleration. You see the auto-tune cavity gives nothing but on cavity. And here we have done some carbon-13 experiment to show that it's really a transfer, and now there's theory to go with it. You can show that you can transfer because all these, it's just like the metronome, all these vibrations are now vibrating in phase. And a solute inside that also has the same vibration starts, of course, it's driven by this thing. Okay, we see this also not only for chemistry, but we see it also for things like superconductors. We can modify the TC of superconductors by the same principle, by putting superconductors in a polymer and driving them. Okay? So this is a very powerful way, but it shows that you can do catalysis. Now, some people think we're the only ones who can do this. No, there's a group in Japan who has 4 orders of magnitude catalytic effect in a cavity. Okay, so this is just an order. So 10,000 times. And you can also modify enzymes. So once we understood this, well, that's great. We can just couple water. Water is the basis of life. We can affect enzymes are full of water. And we chose pepsin. Pepsin is what's digesting your lunch right now in your stomach. Okay? They're eating up, breaking up the protein and cutting it in little pieces so that you can extract the good things from it. It involves water in the active site. It involves water in the tertiary structure, the complete structure. And there's water outside. And we thought, well, this has to perturb it, and indeed it does. Oops. So it vibrates. They're actually water because there are only 3 atoms, have very few modes, vibrational modes. So there are 2 stretching modes, symmetric, antisymmetric, and a bending mode. It turns out that only the stretching modes perturb the chemistry, not the bending mode. That tells you something about mechanistics. Here you see it reduces the activity, but it's still amazing that you can see this on the thing. It's a very difficult experiment. The last thing I'm going to show you is energy transfer. So energy transfer occurs in plants. Okay, actually probably there would be no plants in this part of the world if there wasn't for energy transfer. So the flux of light from the sun is so weak that at the scale, molecular scale, there are not enough photons coming in to drive the chemistry that follows. Physics terms, it's an impedance mismatch. So you have the thing coming in, and there's a rate of photons being absorbed, and the chemistry that follows has to be pushed at a certain rate to be efficient. So plants adapted away from in weak areas where there was little sun by creating antennas and chlorophyll antennas that catch the light and transfer it to a reactive center, thereby increasing the rate by all it took was 300 times. So there's typically 300 molecules, antenna molecules for 1 reactive center to drive the photosynthesis. And this is known as energy transfer, and it goes as first they did the theory, and it goes as 1 to the power over R6, so distance between the molecules. So as soon as the molecules are more than about 10 nanometers apart, this doesn't occur anymore. So we want to see if we can enhance this, because now we have these collective states. So how do we do this? Well, what's very interesting with these light matter strong coupling is that I can couple one molecule, the donor, that one we're going to pump to transfer the energy to the acceptor. We can couple this and make 2 hybrid light matter states. But because they have 50% photonic content, we can use them again to mix with something else. So we use them to couple to accept the molecule, and now we have a 3 hybrid light matter states, and these donor and acceptor are actually quantum mechanically entangled. Okay, so now they are actually like in a they're all talking to each other. Okay, and on top of it, we have this collective effect. It turns out also that this lowest light matter state, called polaritonic state, is mostly acceptor, and the upper state is mostly donor. So you can inject photons in here and see if they come out here. Okay, and that's how you do it. So to make a long story short, this works very well. You can enhance the energy transfer to the limit, practically 1, the rate goes up, and the actual energy transfer. But so that's nice when they're all mixed. But then you can do an experiment which had never been done before, is you can separate the donor and acceptor in space and see if the entanglement plays a role. And you can transfer energy over distances you never could do before. And this is what we did. We put the donors on one side of the cavity, the acceptors on the other, and put a spacer in between. And actually it works very well. You can transfer, I'm not going to show all the time, I don't have time, but you can transfer energy from in this system over distances that are unheard of before. Actually, the theory tells you that there's no more distance dependence. So you're no longer in the Förster regime. Okay? So, I hope I've convinced you that there's light in the dark with QED. Okay, there's something you can do. You can play with this. It's a new tool for chemistry. You can affect reactivity. I didn't talk about dynamics, thermodynamics. It affects the thermodynamics, needless to say, and dynamics. You can also affect material properties. I mentioned briefly, because you have these delocalized states, you can enhance conductivity, energy transfer I just showed you. You can also change superconductivity phase transitions. So we just have we have a paper online which shows that you can change the TC by 50% for C60 rubidium-3, which I worked on when I was young, and you can actually go from 30 to 45 degrees by Kelvin by doing this. If we could do this with high TC material, it would be even more interesting. We've tried, but there is the reverse. When we do this with high TC material, we'd actually lower the TC. Okay? Like YBCO, we lower the TC, but it shows that phonons play a role. So I didn't do this by myself. This is my team of people, and this obviously they did all the work, and this is what every day I wake up, I look forward to meeting them and hearing about the results. So thank you for your attention.
Thank you very much, Thomas, for this fantastic talk. We will shorten the coffee break a little bit because of timing, so please be back here at 15:25, so 5 to half, well, whatever, 15:25. Okay, so it's about time to start the last lecture for today. I have the pleasure to introduce Jennifer Dion, who is a professor at Stanford University. Jennifer actually had her PhD with Harry Atwater and then postdoc with Paul Alivisatos, and both these gentlemen have actually been appearing here 2 years ago on a similar occasion on a Molecular Frontiers Symposium that we had 2 years ago. Well, you can read most of the things that Jennifer says about herself in the little presentation here, but I was intrigued by the statement that you were featured in Oprah's list of 50 wows, and I don't know, maybe I can ask you about that later. That's something that, also that you are a keen educator sort of appeals to me, and so I'm looking very much forward to listening to your talk and to the following question and answer session. So please, Jennifer, take the stage.
Well, thank you so much for the introduction and the opportunity to be here. Can everyone hear me in the back okay? Maybe I'm too loud. Yeah, usually people complain that I'm too loud and ask me to lower my voice a bit. Well, today I wanted to share with you some of my passions. Hopefully in the poster session you'll get to hear about some of my passion for science. I also really love food, I love cycling, and I also love photography. And in the presentation today I want to share with you a little bit about my love of science and photography combined. It's kind of amazing that humans collectively take 1.5 billion photos each day. That is a ton of information with which to learn about ourselves, our community, our history, and where we might be headed. Some of the best pictures can take us to places we've never been before, like this famous image of the supermassive black hole at the center of the M87 galaxy. Yet other images can teach us about our place in the universe, like the famous image of the Earthrise, which in the worlds of Carl Sagan tells us that we're just a pale blue dot, the only world known so far to harbor life, and a place that we must cherish and sustain and learn to treat each other more responsibly and kindly in. Still, other images can inspire us to strive to new heights, like this famous portrait of one of my favorite athletes, Michael Jordan, who famously said, "I have failed and failed and failed again, and that is why I succeed." And I think we heard some of those messages in the Q&A session earlier. And yet other images can teach us what lies within, like this first X-ray of Professor Röntgen's wife. And I think it's images like this that tell us that the future can hold far more promise for medical advances and for advances in sustainability that we can possibly even imagine today. And yet, when we reach the molecular scale, we can't just keep zooming in on our cameras to understand what's happening. Oftentimes we wind up with animations like this animation of a microtubule with a motor protein walking along it. So here the scale bar of the protein is roughly about 10 nanometers, so the protein's 10 nanometers across. And while this animation is derived accurately from the science, it's an animation nonetheless. And when I first saw this animation, when I started as a faculty member, I thought like, wow, wouldn't it be really cool if we could develop microscopies or imaging techniques that allow us to get videos like this, but of actual processes as they're occurring. And that's a lot of what my lab at Stanford focuses on. We try to develop new tools and new techniques to be able to image dynamic nanoscale processes. And in many cases, those techniques rely on combining photons with electrons. So my lab has developed a number of electron microscopy techniques that enable input of various gases or liquids that can react with their environment. In this case, we're looking at hydrogen molecules reacting with a nanoparticle. And by looking at either the electron spectra or the optical spectra, we can get a feeling of how the molecules are interacting at the surface of the nanoparticle and intercalating into the nanoparticle. So here I false colored in red the region where the hydrogen molecules are interacting with the nanoparticle, intercalating in and causing a phase change. And movies such as this, that we can record in real time with near atomic scale resolution, allow us to optimize catalysts and photocatalysts to enable improved, say, energy storage materials or catalytic materials for sustainability. We've also developed combined electron and optical techniques that allow us to look at how electrons and holes are recombining in materials. These are the sorts of processes that are fundamental to solar cells, photocatalysis, and light-emitting diodes and displays. And here, the video that you saw showed how electrons and holes are recombining in 3 dimensions. So just like Professor Hell was discussing earlier, we have the ability to do real-time imaging, but also in 3 dimensions, so doing nanoscale optical tomography. And then we also do some nanoparticle development, and in particular developing nanoparticle sensors of various external stimuli. So in this case, what we've done is develop light-emitting nanoparticles that change color in response to applied force. Now you may wonder, why do you want to have a force sensor? In my own lab, we're very interested in biological forces. We experience forces every time our ears hear, our heart beats, a wound is healing. Forces are also very critical at the interface between our immune cells and pathogens, so they're thought to be quite important in terms of understanding our immune responses. So my group is trying to develop sensors of optical force that work in the nanonewton regime, so that way we can better understand immune responses to pathogens and hopefully develop better immunotherapies. And here's just one example of nanoparticles that are changing their emission color from yellow to red with applied force or with applied pressure. You can see from the transmission electron microscope that they're pretty small, about 20 nanometers across. And then they're also very biocompatible. So as a first case study, what we've done is just feed them to worms. C. elegans, a small roundworm. They chew them up. You can see them here in the digestive tract. And then as they're being eaten, I'll just show you this false color image. You can see the nanoparticles moving throughout the digestive tract, again, eventually being excreted. And based on the color, we can tell what the magnitude of the force is. But more than pretty pictures, I think what these dynamic videos have taught me is how the most fundamental building blocks of matter, namely molecules and photons, are interacting. And from learning about that interaction, we can develop new technologies. And what I want to share with you today is work that my group has just recently started to work on, but we've made some progress on, in using information about light and molecule interactions to develop better pharmaceuticals and better agrochemicals. So to teach you a little bit about the history of this project, I want to bring you back to 2014. I was living in the Bay Area. It was the rainy season. And for those of you who have been to California in the spring, when there's a lot of rain, there are also a lot of snails. And I found these 2 snails mating outside my apartment. As you can see, the snails, or the snail shell, has a certain twist associated with it. In this case, it's a right-handed spiral. So the snail has a chiral shell, namely a non-superimposable mirror image, or twisted shell. And intriguingly, this twist propagates through all the way to the internal organs of the snail, meaning that a right-handed snail is literally only a good fit for another right-handed snail. So you tend to find snail colonies dominated by exclusively one-handedness or one chirality of the shell. Now, like the snail shell, there are many natural materials that are chiral and that have a certain handedness associated with them. That would include DNA, which of course occurs in all natural materials as a right-handed helix. Its non-superimposable mirror image would be a left-handed helix. But like I said, in all natural, healthy organisms, it's just the right-handed spiral. Sugars also have non-superimposable mirror images like glucose and fructose. And again, in all natural, kind of healthy organisms, we tend to find just the right-handed version of the sugar. And also amino acids, the building blocks of proteins, are chiral. Generally, all amino acids are left-handed. Now, this homochirality of nature is perhaps one of life's greatest mysteries, one that many scientists are still trying to figure out the origin of. But importantly, because life and healthy life is homochiral, the presence of an opposite-handed molecular structure can have a pretty profound impact or can signify disease. So if we look, for example, at amino acids, which, like I said, are exclusively left-handed, it turns out that once disease has onset, for example, kidney disease or schizophrenia or Alzheimer's, you tend to find an increased presence of right-handed or D amino acids. So if we can develop techniques to more sensitively detect the presence of right-handed amino acids, we might be able to detect disease at a much earlier onset than we currently can. And just to give you a few more examples about the function of different handed molecules, if we take this molecule limonene, here I'm showing you the organic structure. You've seen organic molecules throughout the talks today. So here each of the vertices corresponds to a carbon atom. When you're synthesizing this molecule in the lab, you could imagine that this last hydrogen, if you're adding it on, could go with equal probability to the right or to the left. And depending upon which way it goes, the molecule will either smell like orange or it'll smell like pine or turpentine. So these opposite-handed molecules can have very distinct functions, in this case for your olfactory sense or your sense of smell. Now, the importance of structure or molecular structure in pharmaceuticals was brought to prominence in the late 1960s when the drug thalidomide was first marketed in Germany. And it was supposed to treat morning nausea in pregnant women, but unfortunately, the other enantiomer, or the other handed chiral molecule, actually induced birth defects and in about 50% of all cases, fetal death. So because of that, in the United States and worldwide, the FDA has cracked down a lot more on better understanding what the side effects of various handed molecules might be. But still, if you look to the pharmaceutical industry and also the agrochemical industry, approximately 50% of all drugs on the market and 30% of all pesticides and herbicides are chiral. And of those, more than 90% are sold as racemic mixtures. Those would include, for example, the drug Advil. Who here has taken Advil for pain relief? Okay, a couple people, or at least a good number of people. So Advil is sold as a mixture of both the right and left-handed molecule. Probably it takes about 30 minutes for you to feel pain relief, and that's because the wrong-handed chiral version of drug basically slows down the efficacy of Advil. So it gets in the way of, say, the left-handed chiral drug interacting with your left-handed amino acids, or the building blocks of proteins, in order to block those pain receptors. And if it were sold as a pure drug, it would only take about 10 to 12 minutes for pain relief in Advil. Also, the antidepressant Prozac is sold as a mixture of both the right and the left-handed molecules, and the wrong-handed enantiomer can give rise to some of the negative side effects, like headaches and heart palpitations. And then in agrochemicals, for example, like the herbicide fipronil, or the pesticides that are common, they can leave residues in soils, giving rise to colony collapse in bees, and organ failure in birds and fish and larger mammals. So why is it that so many agrochemicals and pharmaceuticals are sold as mixtures? Well, it's because, like Professor Ebbison was mentioning earlier, it's actually very challenging to separate the chiral molecules. Essentially, these enantiomers, or these non-superimposable mirror image molecules, are identical in what I'll call scalar physical properties. So because they have the same atomic composition, they have the same mass, they have the same charge, so you can't use conventional techniques to separate them. And for those of you who have done basic chemistry experiments, generally you know centrifugation is a great technique for separating molecules of different weights, right? You just spin them around and the heavier ones crash out first. But you can't use that because they have the same weight. They also have the same charge, so you can't use, for example, a battery or an electric field to separate these molecules. So the only way they can be separated is by coming up with another entity that is handed and that preferentially interacts with the handed molecule. So some of you may have run what's called a column. The typical way of separating chiral molecules in industry today is to run a chiral column where you take your mixture of both the right and the left-handed synthetic molecules that you've made, and then you run them through a tall glass cylinder where packed within that cylinder are silica beads. So you have these micron-scale beads, and then those are functionalized with molecules that's called the chiral stationary phase. So this is a molecule that is made specifically to interact with one-handedness of the drug. So that way, as the drug or the agrochemical passes through, it basically sterically interacts with the chiral stationary phase and gets slowed down. So you can see in this case that the right-handed version of ibuprofen basically would latch on to the right-handed version of this chiral stationary phase, and therefore it would pass through the column more slowly than, say, the left-handed version, which goes through more quickly because it doesn't geometrically interact with that chiral stationary phase. So for each new drug that comes to market, there are companies that have to work on developing a new chiral stationary phase. And often that's a process that can be very time-consuming and very expensive. It's done usually by empirical methods, but it's usually a trial and error process. So this is why many pharmaceuticals and agrochemicals tend to be sold as mixtures, because right now there's still no efficient and effective way of separating chiral compounds. So in my lab, we are interested in light and molecule interactions, and we know that light can also be a chiral entity. So if you think about light as an electric field and a magnetic field that's propagating through space and time, you can simply pass it through a polarizer or a wave plate that enables the electric field to trace out a helix in space or in time. And then when you look at the peaks of that helix, that corresponds to the wavelength of light. Now, if we want to make sure that we're not destroying our molecules in the process of illuminating them, we're generally going to want to work at optical frequencies, so ultraviolet up through near-infrared frequencies. If we start getting to higher frequencies, we might start destroying the molecule. So the key challenge with using light as a reagent, as basically your chiral stationary phase, and separating the molecules is that the wavelength of visible frequency light is much, much bigger than a molecule. So the typical wavelength of visible light is between 700 and 400 nanometers, and the typical size of a molecule is on the order of a nanometer, or up to a few nanometers for some of the proteins. So that's one of the challenges. Another challenge is that most molecules are blind to the magnetic field of light. And the key reason why that's really important is because enantiomers are basically electric dipoles and magnetic dipoles. And the key thing that distinguishes them, or that makes them non-superimposable, is the direction of their magnetic dipole. And to kind of conceptualize that a little bit, maybe you can think about that helix of DNA again, where you can think about the z-axis of the helix as being the electric dipole, and then you know that magnetic dipoles correspond to current loops. So if you think about the loop of the helix, for one of the enantiomers, that helix is going to the right, whereas for the other enantiomer, that helix is going to the left, and that corresponds to completely out-of-phase magnetic dipoles in the simplest of chiral molecules. So we need to come up with ways of correcting for that size mismatch between molecules and light, and also for enabling light, or the magnetic field of light, to interact more strongly with chiral molecules, so that way we can better distinguish them or use light to initiate kind of an optical handshake with one enantiomer. So how do we address that? Well, we use nanostructured materials. I'll call them loosely metamaterials just for historical reasons, but you might find them in the literature called metasurfaces or Me resonators. Broadly, though, I just mean nanomaterials that have optical frequency, electric and magnetic resonances, and that act as nanoantennas to focus light down to the nanoscale. So here's one example, the one that Oprah got excited about, these so-called negative refractive index materials. This is just a simulation of negative refractive index water. And you can see that the straw gets bent the wrong way. You also can't see the bottom of the glass of water. So these negative refractive index materials have a lot of interesting and unusual properties. And the key way you get that is by tuning both the permittivity and the permeability. So we saw earlier in one of the talks that the speed of light was related to the permittivity and the permeability. Basically, the product of those two, epsilon and mu, square root, is the refractive index. So to tune the refractive index, you need to tune both the magnetic response, which corresponds to the permeability, and the electric response, which corresponds to the permittivity. Now, we're not going to be focusing on making negative index materials per se, but we do want to have that magnetic response, and that means that we're going to be working with materials that essentially tune what the effective optical index is. And the larger the optical index is, the smaller the wavelength of light is. Here I'm just showing you one example of a metamaterial. It's a colloidally synthesized assembly of, in this case, small metallic nanoparticles that are arranged around a silica sphere. And the size of this structure is much smaller than the wavelength of light. So that way, when they're dispersed in water, they essentially act like artificial atoms or artificial molecules that can control light. And here I'll just show you one of these structures. You can see the scale bar is 30 nanometers, so this structure is about 100 nanometers across in total. And you can see that the magnetic field is strongly enhanced within the core of this particle. We're just looking at a cross-section of it. And you can also see that the electrons in the metallic nanoparticles are tracing out kind of these circular displacement currents, which is what's giving rise to that strong magnetic field. So this set of structures where you essentially use either metals or dielectrics that are nanostructured can help us shrink down the wavelength of light and also can give us strong magnetic light-matter interaction. So essentially, these materials exhibit optical frequency magnetism. Now for this talk, I'm going to focus on a slightly different nanostructure. I'll call it a coaxial cable. It's a lot like the coax that you would plug into the back of your cable television, but shrunk down by many, many orders of magnitude. And it's comprised of a metallic core, a metallic cladding, a dielectric channel, and then circularly polarized light will enter into the dielectric channel and essentially excite collective oscillations of the electrons at the metal dielectric interface, and then the light will be scattered away from the structure so that it can interact with the chiral molecule. And when you arrange these nanostructures in an array, you again wind up with a metamaterial, or basically this periodic nanostructured material that gives you control over the local refractive index as well as the electric and magnetic fields. So the vision in terms of separation, or one vision that you could think of, is to have an array of these coaxes essentially arranged as a film. And then when you illuminate this array with circularly polarized light, what the mixture of enantiomers winds up being separated by virtue of this optical handshake that's initiated between light and the molecule. So in this case, the right-handed enantiomer gets attracted towards the coax. And I'll mention that this technique is actually quite generalizable. So we did it first with this metal dielectric coax, but now we're doing it with nanostructures that are more amenable to packing in the column. So that way you don't need to have that chiral stationary phase. You can just illuminate your column with a series of LEDs and then have the nanoparticles have those optical frequency electric and magnetic resonances to attract one-handedness of the molecule towards that structure. Okay, so can we make this particular structure and show that it exhibits optical forces that are preferential based on the handedness of a specimen nearby? So we use a technique called focused ion beam milling, essentially focused gallium ions that allow us to mill away tiny little structures in the metal. Here you can see the coax, so we have the metallic core, the metallic cladding, here's the dielectric channel, and then we also patterned a grating around the coax, actually inspired by some of the earlier work of Thomas Edison, in order to increase the transmission that's coming through the coax. And if you zoom in a little bit more to that coaxial array, you can see the dielectric channel is just about 30 nanometers across, so about the size, or roughly half the size, of a virus. So now let's look at some calculations of how light would interact with this coaxial structure and how that light would interact with the chiral specimen above it. So this is a calculation basically solving Maxwell's equations and trying to figure out what the pulling force would be of light that has exited from the coax on a right-handed structure that, for simplicity, we just assume is roughly a 5 nanometer sphere with an electric dipole and a magnetic dipole that's close to what you would find with a molecule. So you can see for this right-handed structure with right circularly polarized light, the pulling force is uniformly distributed around that dielectric channel. So we get the strongest optical force interacting with that chiral specimen when the chiral specimen is above the dielectric channel. You'll notice that the pulling force is about 2.5 piconewtons. That's not a very large force when you think about, typical forces that we're used to working with, for example, Newton scale forces to weightlift at the gym. But it turns out to be large enough to exert a significant force on molecules and to separate them. And of course, force is a vector, so if we plot not just the magnitude but also the direction of the force, we can see that regardless of where the molecule is going to be in space, it's always going to be attracted towards the coaxial structure and eventually pulled through it. Now, if we compare this with the left-handed structure, you can see that the pulling force is quite a bit weaker. And then if we look at the direction, that pulling force is also repulsive. So the molecule will actually get repelled away from the aperture, giving rise to that physical separation that we had envisioned. So how can we quantify these forces and see if our calculations hold true? Well, we use a technique called atomic force microscopy, where we take a nanostructured pyramid of either a dielectric or a metal, or as I'll show you later on, a molecule, and then we put it on a cantilever. It's essentially like a diving board that we're scanning over the surface of our nanomaterial or a metamaterial. And based upon the optical force, this whole cantilever plus the tip on it will either get deflected towards the sample or away from the sample. And what you do is you can bounce a laser off the end of this cantilever, and based upon whether the laser moves down or up, you know whether your tip has moved down or up and therefore is attracted or repelled from your structure. So it's a really powerful technique. People have used atomic force microscopy to map out with very high resolution the structure of materials with near atomic scale resolution at this point based upon the sharpness of the tip. But we wanted to use it to map out these optical pulling forces. So what we did as a first proxy for a chiral molecule is we just patterned a spiral at the end of our atomic force microscope tip. So this spiral is a lot like those snail shells I showed you at the beginning of my talk. In this case, we have a right-handed spiral. And when we turn the light on, we can see the tip gets deflected down towards the sample. And when we turn the light off, the tip remains in its stationary phase. So in this case, it's a certain height above the coaxial structure. And we're just turning the laser on and off. And we can measure the pulling force because we can measure the laser deflection coming off that cantilever. Here we're just illuminating the coax at one particular wavelength. This corresponds to the resonant wavelength of the coaxial structure, which is where we'd expect to see the largest forces. And then because we have that sharp tip, what we can do is scan it over the coax. So in this case, we're scanning it over just one quadrant of the coax, so we can get slightly higher spatial resolution. And when we have right circularly polarized light illuminated on this right-handed AFM tip spiral, we can see that the pulling force is quite symmetrically distributed and large, whereas for left circularly polarized light, the pulling force is much smaller. So we can quantify those pulling forces as a function of the separation from the coaxial array to the chiral tip. And what we see is that For left-handed illumination, the pulling force is always repulsive, so it's positive, meaning the tip gets deflected away from the surface. Whereas for right-handed illumination with our right-handed spiral, the force is always negative, meaning it's always attracted towards the sample. So this is kind of the crux of this part of the presentation, showing that circularly polarized light can exhibit preferential forces on enantiomers. And in addition to swapping out the light, we can also just swap out the spiral pattern that we mill for the right or left-handed versions to show that we get similar results. We're not just limited to doing this on AFM tips. We can do this on molecules, and as a test for whether it worked on molecules, we were able to attach just a single DNA to the end of our AFM tip, and then we could again sweep the separation between the coaxial fiber and where the DNA was. And we can see that when we're in the near field, or when the molecule is quite close to the coax, it gets attracted to that channel. Whereas we're in the far field, so at separations greater than 300 nanometers away, there's very minimal interaction. So 20 base pairs of TNA is a 4 nanometer molecule. So this is getting us closer to the regime where we can start working with pharmaceutically and agrochemically relevant molecules. So this was a metallic structure, and you probably saw that the resonant wavelength we were working with was in the red, so at 770 nanometers. In addition to getting this to work for smaller molecules, we need to be able to scale the wavelength so that way our structures are resonant where the chiral molecules are also resonant. And for most pharmaceuticals and agrochemicals, that tends to be in the ultraviolet regime. That's where you'll have electronic resonances in your molecules, or electric and magnetic resonances. It's largely because in the pharmaceutical industry, they don't want to design the drug to have a color associated with it, because when you excrete the drug, you might panic if it came out bright pink. So it makes our life as physicists a little bit more challenging, but we can work with materials that have resonances in the ultraviolet regime. And these are actually some of those nanoparticle type structures, so we could imagine packing a column with these nanoparticles and then just changing the geometry of the nanoparticle in order to be able to selectively trap or slow down a particular new drug that comes to the market. And then in certain cases, people are also interested in using vibrational modes to separate molecules. So this is why I think I was paired up with Thomas Ebbison. It's kind of a nice complement. So we can also design materials that work better in the infrared regime, so we can target vibrational modes and therefore wind up separating molecules by illuminating them with circularly polarized light and separating them by resonantly exciting a vibrational mode, causing one enantiomer to have a lower molecular weight than another by virtue of bond breaking. And then as my final slide, I'll just share with you how beyond just sorting chiral molecules, we can also use these structures to direct enantiopure syntheses. So generally, when you have an organic synthesis, it's quite challenging to develop a chiral catalyst or a chiral synthesis, one that preferentially just gets you, say, the right-handed molecule. But with these nanostructures, we can take a synthesis that normally would just be, say, the reactants yielding equal probabilities of the right and left-handed molecule, and giving rise to, for example, just the right-handed molecule. And here you can see what the yield would be for a particular reaction as a function of the enantiomeric excess. So experimentally, people have actually done this with circularly polarized light alone, and they can get pretty high enantiomeric excesses on the order of about 10 to 20%, but they wind up destroying most of the molecules. So for a high enantiomeric excess, you wind up getting a low yield if you just use circularly polarized light. But with some of the nanostructures that are designed to direct the synthesis, we can get high yield with higher enantiomeric excesses. So we're approaching the point where this technique can compete with industrial techniques like chiral catalysts and HPLC or chiral columns. So with that, I'll summarize. in the beginning of my talk, I shared with you just some of my favorite images, and those kind of inspire my work in the lab. Stefan Hell was saying earlier he's not a microscopist. I do kind of consider myself a microscopist, or maybe better, a nanoscale videographer. I really love capturing videos of the nanoscale, because I think if you can see something, you can better understand it, and then hopefully better improve it. And by combining electronic approaches with photonic approaches in generally what I'll call a nanophotonic approach, we can get a lens into these dynamic molecular and nanoscale processes. And then from those lenses, what I've learned is how to better control light interactions with molecules. And hopefully you're walking away with a message that light might just be the next handy reagent for pharmaceuticals and agrochemicals. We're not used to thinking about light as something you can tweak in your chemical reaction, but I hope you'll walk away with that from my talk. So by using light combined with nanostructures, we can enable both high-sensitivity chiral sensing to detect trace amounts of opposite-handed amino acids, and we can also enable low-cost separation and potentially enantiopure syntheses of chiral molecules. You can think about this, like I said, as light initiating an optical handshake with chiral molecules, or going back to our snails, perhaps a little optical smooch that hopefully enables safer pharmaceuticals and agrochemicals and a healthier planet and population. And with that, I'd like to make sure I acknowledge all of the students and postdocs who have made this work possible. Those of you thinking about being a scientist, I can't imagine a better career. It's not only a lot of fun every day in the lab to be able to interact with extraordinarily bright coworkers and colleagues, but it's also a job that gives you the opportunity to travel the world many times over. Here I'm showing you some pictures with some of my students and colleagues, role models. Recently I was in Singapore, which was a lot of fun, and then these are some of my groups throughout the ages. So thank you so much, and I look forward to the Q&A session.
So thank you very much, Jennifer, for this vivid presentation. So there is now time for the Q&A session. So please, Thomas, if you join Jennifer at the stage. And please, if there are questions to the two last speakers, you can start.
Do you need water?
I'm okay.
Queuing up. So hopefully you didn't run out of questions. Not right just yet. So we have a question.
So I'm Helen from London. And I'm just asking, because both of you mentioned methods to separate, like handed molecules in different ways. One was the help of basically electromagnetic fields or something that matter, and the other one using a combination of light and nanomaterials. And like, in a weird sense, like, what do you think is most viable and like why?
Great. So I think the question was, in using light to separate molecules, which do I think is more viable?
Okay, sorry. So basically, the last presentation mentioned how, like, by having the molecules and by making reactions happen in the vacuum, it could, and by switching the wavelengths, like, not quite, but I'm not really finding words here, sorry.
Oh, yeah.
Yeah, you could, like, turn the like, yield from one side to the other.
Oh, yeah, yep.
Yeah.
So maybe I'll focus first on the kind of separation, which is more like the conventional industry technique with the column.
Okay.
What you could imagine is when a pharmaceutical company makes a chiral drug, which is generally going to be a mixture of the right and left-handed versions, they'll have a solution, and they can measure the optical absorption of that solution. So they'll know, okay, this has, you know, a resonance at 250 nanometers or 380 nanometers. And then you could have a column where the nanoparticles are designed to be resonant at that wavelength, and then you just illuminate with LEDs that have filters, at that wavelength in order to be able to separate them out. So I think that would be the path that I see as probably being most tractable in the short term. In terms of the synthesis or directing the synthesis of chiral compounds, the physics is really interesting, and Thomas Edison may actually have some input as well. Like essentially you are, kind of like he was doing with vacuum and with his cavities, we're using these nanophotonic structures that have a relatively large, it's called a quality factor. They store light for a long time, but at the nanoscale, and you're essentially changing the energy landscape or the reaction coordinate to make it preferential to go one way versus another.
Yeah.
But you saw, like in that plot, even with some of the structures we're looking at, we can increase the yield in the enantiomeric excess, but ideally you want that curve to be almost square. So maybe you want to comment on that.
Yeah, it sounds very loud, but I actually, when I listened to you, I thought, well, we actually have chiral cavities. So obviously one could use, we could try to use the vacuum field. We could try doing that together. It might be a lot of fun. I didn't realize that you could actually do this the way you're doing it. So one could combine, so you don't need any light. Anything that involves light on an industrial scale is very expensive, but the vacuum field is available everywhere. So if we just need to have cavities that respond, that are chiral, and that you can design, that's easy to design.
Okay. So the cavity method could potentially be cheaper as it doesn't require light?
Sorry, it's hard to
Could the cavity method, potentially be cheaper as it doesn't require light, basically?
Yeah, I mean, if it does what Jennifer is finding in her experiments, if it does that with the vacuum field, it's certainly a simpler thing. So then, of course, the cavities are very tiny in our case, but actually we are already collaborating with industry.
Okay.
Okay, because it is, you can scale it up, multiplex it, and then you can actually prepare molecules in tiny cavities.
Thank you both for your answer and your speech.
Thanks.
Yes. Okay, I have another question for Professor Ebbesen.
Yeah.
You've raised the subject of ground state several times. What is your opinion on the ground state of the Higgs particle, quantum tunneling, and vacuum decay?
So I'm a bit hard of hearing. I'm not so young,
Okay,
so can you repeat it?
Should I take the entire question from the beginning?
Yes,
or?
please.
Yes, okay. You've raised the subject of ground state several times. What is your opinion on the ground state of the Higgs particle? Quantum,
Higgs particle?
Yes, the ground state of the Higgs particle, quantum tunneling, and vacuum decay.
Emmanuel, where are you? No, I do not have any opinions on the Higgs particle. It's a boson. It carries, like all bosons, carry forces. But otherwise, I have no opinion on the Higgs boson.
Okay.
I would love to get involved in something like that, but I would have to understand a lot more physics. Okay, and I don't.
I'll just go, right?
Yeah, thank you.
Hi, my name is Julia Wang. I'm from Turing Gymnasium here in Sweden. And my question is to Professor Ebbesen. Because you mentioned it in the beginning of your presentation, I've been wondering how does the charges, like positive and negative charges, work with space?
Okay, so I'll tell you a little story attached to that. When I was about your age, I was in college, a little bit older, at the university. I asked the physics professor, in a physics exam, we were allowed to ask a question, a free question. And so, which was given I don't know, 10 points out of 100. And I thought, I always wondered how positive charges or negative charges recognize each other to make attractive forces. So I asked that. That's the question I would like to ask a physicist. We were asked to ask such a question. And the professor told me, nonsense, and gave me 0. Okay? Now, many years later, one day I met some very well-known physicist in a party in Princeton, and he said, I asked him the same question, and he said, of course we know what it is, they're exchanging photons. So what positive and negative charges are doing is that they're exchanging virtual photons. all electric and magnetic forces are carried by photons. I didn't know that. And what makes the difference between repulsion and attraction is a phase issue. So imagine you and I are throwing a ball to each other. It's a virtual photon. I throw you the ball, and you go backwards because it's heavy. That would be repulsion. And of course, it's a bit more complicated because it's quantum physics, but it's a phase relationship that actually determines whether there's attraction or repulsion. So when you put a magnet on your fridge, just remember it's exchanging photons like mad with the fridge. That's kind of amazing to me, but that's the beauty of the world.
May I ask another question? Okay. You mentioned also that the vacuum fluctuation is possible to be detected, and I was wondering how you actually do that.
Sorry, can you repeat that?
You said that when you were mentioning how the history about vacuum fluctuation, you said that it can be someone has researched it and detected vacuum fluctuations.
Or how do they measure vacuum fluctuations?
Yeah.
I don't measure them. I'm not good enough for that. But there are some very clever physicists in Constance and in ETH who do this, and their students. They actually look at their very high, very fast spectroscopy techniques, a very short laser pulse, and associated with a nonlinear material. And because on average, the fluctuations cancel out any place. On average, on a fairly large scale, but microscopically and time resolved, locally it will go in one direction or the other, the fluctuations, and induce a change in the material that will combine with the pulse and show up in a nonlinear experiment, nonlinear optical. Will add up to another pulse. So you imagine a fluctuation, a laser pulse comes through, there's a fluctuation, and they either will add up in one way or the other, and that you can detect. And that's how they do the experiment, apparently, from what I've understood. I visited 1 or 2 labs, and that's apparently how they do it.
Okay, thank you.
Welcome.
Hello, I am Gian from Procivitas Växjö, and I have a question for you, Leon. So, you mentioned that a problem you face is that light often has a too large wavelength to affect certain molecules. Isn't it possible to simply use light with shorter wavelength in those cases, for instance, gamma rays or X-rays?
Yeah, that's a great question. So if you work with light that's of too high energy or too short a wavelength, you can kind of destroy your molecule in the process. So that's one reason to not work with too small a wavelength. We also want to design materials where they have their resonance, or kind of their resonant frequency or resonant wavelength, matched to the molecular resonance. So most of the molecules that are industrially relevant have resonances roughly between the 200 to 400 nanometer regime at optical frequencies, and then there are also some vibrational resonances in the mid-infrared. So that's kind of the wavelength that we're targeting our structures to have resonances at, so that way they're matched with the electric and magnetic dipoles of the molecules.
Okay, thank you.
Hi, I'm Sarah from Johannes Hedberg University in Helsingborg, and I would like to ask Professor Dian 2 questions, if that's acceptable. My first question is, what properties causes the molecules to be repulsed versus attracted to the coaxes, which you mentioned earlier? Is it related to the poles?
Yeah. Oh, that's a great question. So you can think about this like an optical force, and if you start from Maxwell's equations with the electric and magnetic fields, you can actually calculate the force that an object would feel with light. And this is the basis for optical tweezers. You might have heard about optical tweezers where you can use focused laser beams to manipulate objects. Generally, the force is proportional to the gradient of the field, the gradient of the electric field. But if you work through the math, assuming that your object has both an electric and a magnetic dipole, you also wind up having a second term that either adds or subtracts onto that first term that's based on the handedness of the electric and magnetic dipole. So you can essentially play around with the nanostructure to tune the magnitude and the sign of that second term that makes the overall force either positive or negative. And when the force is positive, that would correspond to, say, an attractive force. When it's negative, that would be a repulsive force.
Okay, and my second question is, you mentioned that we might be able to detect opposite-handed amino acids to detect diseases early on. Could you tell me how that would be done? Are you?
Yeah. So I think that one is almost a little bit easier to understand. So essentially when light comes in and interacts with these nanostructures, you wind up locally enhancing the electric and magnetic field compared to what you would have in free space. So the photons essentially want to reside near these nanostructures. And you can design the nanostructures in such a way where the local electromagnetic field also has a certain handedness associated with it. So as long as you build up enough field of the right handedness, you can detect trace amounts of that handed molecule. So it's almost an easier experiment to do. It's the one that we've started off doing first. So we can detect very small concentrations of, say, the left-handed enantiomer in a predominantly right-handed mixture.
Thank you very much.
Hello, my name is Tim, and this question is for Professor Ebbesen. You speak a lot about virtual photons, and I was wondering if you could define the photon.
I wish I could. I mean, I've asked physicists if they are real, and they said yes, they're real, and you cannot say that virtual photons are not photons. So I actually do not know. There is maybe Stefan or Emmanuel, if he's still here, knows the answer to that. I actually don't know anything beyond that, but they do exist because otherwise we can't explain the forces. I can't say anything more about it. They leave a momentum trace. So it's like vacuum fluctuations. You see no net electromagnetic. There's no energy coming out of the universe unless you, for free. There's all this it's background fluctuations. But you can see the momentum trace of fluctuations. And I suppose maybe virtual photons also leave a momentum trace. But I don't, and that's why they play a role in attraction and repulsion. But I don't know anything more about it. And I don't know if you really need to ask a quantum physicist.
So it's more of a term to, when you're speaking about interaction between charged particles.
Yeah, and between magnets. Okay, that's what I was saying before. You put a magnet on the fridge, it's exchanging virtual photons like mad with the fridge. You don't see them, but they're there. They're playing a role. It's just like Higgs particle. Why do people look for Higgs boson? Because of gravitation, so they realized there had to be something carrying the force. Force are carried by something, always.
Thank you.
Welcome.
I'm Vilgot from Pilskolan, and my question is for Professor Ebbesen. You said you used the screwdriver to tighten the thing. Is there not a lot of room for human error in that?
Yes, you have to have the touch. So no, actually, it's kind of easy because the polymer is pretty rigid, so you have to force. Now, what happens is that to film, the two cavities distort actually under the pressure. The glass, the windows, are actually the real problem. They distort. So if you see on the video, we put a little cush, and it's only in the center of the cavity that it's perfectly in tune. And therefore, that's where we analyze the chemical reaction. And it's faster than diffusion. We've checked all these things. There are a lot of things that are not said that I didn't talk about, but it's okay. It's very easy. There are other groups in the world now who have little micrometers, and they have made much more sophisticated thing than just a screwdriver. It works.
Okay, thank you.
You're welcome.
Yes,
yeah.
It is. I have sort of a combined question. My name is Manny. I'm from Växjö.
Sorry?
My name is Manne.
Yeah.
I'm from Växjö, southern
Yeah.
part of Sweden. So like an echo. So you mentioned earlier that, like in your talks, that your research, Jennifer, could implicate these different forms of molecules, and you had different examples of what your research could implicate in, like, practically. And so I wondered what might the combination of your two fields do for practical implications.
The combination of the two things?
Yeah.
What they could do? Well, if we combine Jennifer's separation technique with microfluidic, use the vacuum field, that could really be useful for pharmaceutical industry. Okay, surprisingly, what I didn't know, because I'm not a synthetic chemist, and so I look at synthetic chemists with great admiration, but there are plenty of reactions that are used industrially that are very inefficient still, even after hundreds of years of 100 years or 150 years of chemical engineering. And all the techniques have been exhausted. All the standard approaches have been exhausted. And that's what they tell me. And so they want to see, for example, if even in our microfluidic structures, if they can overcome some of these problems and increase the yields. Similarly, if you can, for pharmaceutical industry, obviously, being able to separate left and right is a critical thing, as Jennifer explained. And so if I can combine, play on the chiral vacuum field, which is what little devices we have made, and combine it with the sort of approach that Jennifer is doing, maybe we can do something revolutionary for the pharmaceutical industry. That'd be fun.
It sounds very interesting. Thank you.
Yeah. You're welcome. I think you'll hear some interesting talks later on too, or if not, you should at least track down Professor Hollis, who's done some really neat work too on using light matter interactions for product selectivity. So in my case, I focused mostly on a subset of products that are chiral, but she's been able to show how she can tune various reaction pathways to give rise to particular products based on how electrons are being injected into the final molecules that are being formed. So.
Thanks.
Okay, so I don't see a line anymore. Maybe the poster session is getting closer. Is there anything that you didn't get asked that you wanted to get asked?
No, I think...
this is a typical question to students. But,
maybe I'll ask you a quick question, because all the students are here.
Yeah.
So you're probing the reaction, dynamics or pathway using IR spectroscopy. Is that right?
Yeah.
Or so
or visible, both.
Okay, so to what extent does that light modify?
No, because
we
do the IR is a pulse, the FDIR is a pulse thing, so it just does it once in a while.
Okay.
Yeah, a very weak pulse, it's spectroscopy, otherwise we couldn't do spectroscopy. But very often we just run the reaction, it runs for hours, so we just take a spectrum once in a while, and it's running, we're just checking, or we do visible. The most common thing, many of these reactions are fall in the visible, and so there's no absorption, there's some emission, and there's no IR strong coupling. There's no, we're not sending light in where the IR is, so there's no direct link between the two.
Thanks.
So, thank you. With that, the scientific program here is ended, and we're going to have a poster session, but I will leave the microphone before you rise to the organizers.
Hello. So, in fact, the only ones who can stay in here are the students, high school students and speakers. The rest of you will go to a poster session, and actually we have an exciting format where poster presenters have 60 seconds to present their poster from a stage there. So grab a drink and some snacks and gather around the stage, and you will get some quick science. For the students, you stay put, and we will fix you up on stage soon.
dinner? We meet before or how
No, we
Yeah,
meet
we go
7:30 at
7:30
Fiskekrogen. You know
Fiskekrogen.
Fiskekrogen?
Yes,
Yeah.
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 Just to know. Thank you.
Okay, very nice.
Say goodbye. Thanks.